works? All right. of today, and it includes our invited talk, and it's my great pleasure and honor also to introduce Manuel Hermenegildo. And I should start by mentioning that he's an ACM fellow. He was elected last year, and this is an award for the top 1% of ACM members, and awarded by nomination to people who have distinguished themselves both in their research achievements and in their contributions to the computer science community. And I have no doubt that Manuel qualified adequately, more than adequately, in both counts. So for the last 30 years, after obtaining his PhD from University of Texas at Austin, he's been a leading figure in logic programming, constraint logic programming, parallel programming, program analysis and transformation, programming environments, and program development environments. And he's a professor at Technical University of Madrid, and also the founding director of IMDEA Software Institute, which he built up into a world-leading research institute in the 10 years that he was the director. Now, I could go on, but I decided to ask for expert opinion in introducing him, so I asked ChatGPT to write me a little poem, and it generated 6 rather poor verses, but actually a couple of them captured very nicely some of what I wanted to say. So one verse is: a mentor, a guide, a visionary mind, to his students a beacon forever kind. In the world of algorithms, he's a luminary star, a famous professor, revered near and far. From prologue's mysteries to AI's grand design, in algorithms and data, he's a paradigm. That doesn't really rhyme, but a mentor, a scholar, in his wisdom we confide, for he leads us on the path where brilliance does reside. So with that, I would like to introduce, I think Manuel's talk will focus, or at least the themes of program development environments and analysis of programs will be in the fore in his talk, which is entitled On-the-Fly Verification via Incremental Interactive Abstract Interpretation with ChowPP and Verifly. So, Manuel, over to you.
Well, thanks very much, John, and thanks very much, ChatGPT, of course, for giving us such a hilarious contribution. That's a lot of fun. Okay, so on-the-fly verification, that's the objective. It's work done with Isabel, Jose, Pedro, Louis, Daniela, and Daniel, some of which Pedro and Jose and Daniel are here. And it's a real honor. Thank you very much for inviting me to give this talk. Hope I can present some fun stuff to you. It will be a little bit of slides and then some demo. I mean, for the fun factor. So the objective is to analyze and verify software projects interactively during development. What for? To detect bugs, to verify assertions, and to do this on the fly in the editor. Of course, you can also do it at commits and so on, but the concentration here is to do it in, while you're editing the program. And the problem, of course, that you have is that the precision that you need to be able to do, significant verification and to get significant results, which typically requires context sensitivity, complex domains, and so on, can be quite expensive. No? So we address these issues in our tool with several techniques, and I'll try to talk about some of those. The first one is to have an efficient context and path-sensitive fixed point, the top-down algorithm of the Ply analyzer. I'll talk a little bit about that. So this, start with an efficient analyzer that has the precision and can get this precision efficiently. Incrementality, fine-grained incrementality. But our work on incrementality was originally not exploiting the module structure. Then something that we've done more recently, all the other stuff is relatively old work, very old work. What we've done more recently is to combine modular analysis with incrementality, which is what you need to really scale and do this, make this a reality, and the ID integration, which is the fun part, which I'll try to show. We try to do this, well, we're Prolog people, we love Prolog, we do it for Prolog, but we also support other languages via translation to constraint horn clauses, also known as Prolog or CLP. And we try to cover in this verification objectives, covered both functional and non-functional properties, so types, pointers, aliasing from pointers, shapes, recursive data structures, things like intervals or numerical domains and so on also, and then the non-functional properties like time, memory, energy, gas, etc. Now, how did we start? A bit of going back to the beginning, which also because we're in Lobster and people are familiar with this. In the 90s, languages were mostly statically typed, and that was the religion, let's say. We had ML and Haskell, and in the logic program, that from the functional programming side and the logic programming side, we had Gödel and Mercury. And in that context, a bit also in the view of Mercury, of how Mercury was and the things that it had to give up from the traditional logic programming to achieve the goal of verification, we developed the Chow language, Chow Prolog language. The idea was to provide, of course, a very good Prolog. That's our main objective. But in addition, so it's a Prolog that has extra stuff. And the main thing is that we try to provide the flexibility and the fast prototyping of a dynamic language, as we love, and somehow to also give the guarantees of the strongly and static and strongly typed languages. So somehow our objective with this system and with what we've been doing for all these years is to bridge the gap between dynamic and static languages. In that sense, I mean, probably, I think that Chow Prolog was the first dynamic language with safety assurances, so something that is now very popular if you think of, TypeScript or all the additions that they are doing to Python and so on is sort of the same idea. What are the keys of the approach? The first one is to have assertions rather than strong types or traditional types. Types have evolved, of course, and we can talk about that in the questions maybe, but to have assertions, have the assertions be optional, to not restrict the properties that you can talk about in the assertions, and therefore accept undecidability, your type system, your inference system, your abstract interpreter has to deal with undecidable properties. And that takes us, of course, to having to deal with approximations, but safe approximations, and that leads us to abstract interpretation-based verification. So the idea of abstract interpretation-based verification, we wrote a very early paper on this, is that you can, all your tasks from verification, like determining correctness, completeness, incorrectness, and incompleteness, so verifying and finding bugs, can also, thanks to very good ideas from John, can phrase in terms of comparing your intended semantics with abstractions or of your intended semantics in an abstract domain with abstractions of the concrete semantics and developing sufficient conditions for this verification. This is not talk to go into this, but now to be able to do this, to be able to have an approximation, an over-approximation, sorry, or an exact approximation or an under-approximation of the meaning of programs, you need an analyzer, and for that we developed, actually was motivated by parallelizing programs, but we had it, a framework for program analysis for abstract interpretation, which basically takes a set of horn clauses, constraint horn clauses, and some abstract domains, and calculates a safe approximation to the meaning of the program in this abstraction. The algorithm is essentially an efficient, incremental, abstract OLDT resolution. So it's a resolution algorithm with tabling. It's sort of the original top-down algorithm. I think we came up with this algorithm, and it's pretty much, it's the algorithm used in many analyzers nowadays. And the components are, one of the main components is that make it efficient is first using memoing, using a call answer table where you store multiple entries for each block. You store the call pattern and the success pattern, and you store several call and success patterns per block, where the success patterns or the exit states are they abstract the exit states for a particular entry state into the block. And or if you want to think about it as preconditions and postconditions. And this is probably what we would call now summaries, for example, if you have several of them and so on. And then you have a dependency arc table, very important, that basically links these table entries so that you link the answers for a call A to the answers of a call B, so that you know that if the exit for a call B changes, then A will also change. And therefore, you track dependencies in this way. This gives you context and path sensitivity. Path sensitivity because this dependency arc table, these links basically abstract the paths to the program. They abstract them as regular structures, or as grammars. No? And then you get multivariance. You can have several versions of procedures or blocks. You get program point info because each one of these call answer tables corresponds to program points. You get efficiency because of the memoization and also because of the dependency tracking, because this dependency tracking allows you to optimize the fixed point and converge much faster. You also construct the strongly connected components on the fly, take advantage of the base cases and so on. You have genericity in the sense that the abstract domains are plugins, and also the widenings, for example. And of course, it handles mutually recursive methods, library calls, externals, and so on. You can guide it with assertions, so there's a mechanism for saying when it loses precision to provide information to guide it. And it works with modular, and now, well, it used to work with modular programs and with incrementally, and lately we've managed to combine these two things, which is what I want to talk about. Okay, so the analyzer basically takes a source program, just a set of constraint clauses, having constraint horn clauses. It analyzes and it gets some information, which is true information. We call them true assertions. So that's what comes out of the analysis, true assertions. And this can be recursive types or shades, pointer aliasing, as I said before, constraints, and things like determinacy, non-failure, cost, sizes, termination, anything like that. Then that information is compared to the assertions, to what we want to prove. This can happen as a separate process or inside the static analyzer. It doesn't matter, but we depict it here separately for clarity. And the result of that can be that the assertion is checked, and then you have verified the assertion, and you also have a proof. This is very important. I mean, so you get a proof that the assertion is false, and then you have found an error statically, all this is static, or, and this is what non-desirability brings you, you may not be able to prove it, and you have to live with that. Now, what do you do in those cases? Well, in our approach, when you have an assertion that does not, you cannot prove it at compile time, you cannot prove it statically, then we turn it into a runtime test. So at least we get dynamic safety. What's maybe called dynamic verification nowadays. So, and now this is important for this to work. For the fact that your assertions can be checked at runtime, your assertions have to be runnable. Now, most systems either have runnable assertions, but they are not checked at compile time, like in C, the asserts in C and so on, or more traditional systems, I should say. Or you have assertions that are proved by theorem prover statically, but have nothing to do with runtime. Of course, these things have evolved, and now we have dependent types, and we have all these things, but this is the original model, no? And, but of course, then for that to work, your runtime, your properties that appear in assertions have to be runnable, so you can actually check them also at runtime. So I'll talk about that in the demo. So this is something that we proposed, as I said, in the 90s, in the mid-90s, and it's a true precursor of all the gradual and hybrid typing approaches that we have nowadays. Now, the other aspect, is that in order to support different source languages, we propose to do translation into horn clauses. So the idea is that you take, if the source language is in a different, the source program is in a different language, then you translate it to horn clauses. This is what we mean by this, the check, false, and check. This is an example, a very, very quick example of a filter. This is a filter from a company actually, from XMOS. And here we have a pragma that says we want to check some energy consumption. And then this is exactly the assertion that goes into the static checker, and that we combine with the true information, which is this one, that comes out of the analyzer. That tells us that the actual energy consumption is larger than 3.35 times elements. Elements is an input parameter here of the program, plus whatever, and this. So it's between this upper and lower bound. And then when we do the check, we end up getting two of these results, because you can get multiple results. So you get, thanks to a great idea from Pedro, to divide this into by segments, intervals. So you get parts, values of elements for which the assertion is checked, and values of elements for which the assertion is false. So anyway, this is to put more in perspective the idea of how it works and how it works on this is an imperative program, and actually the analysis is done of a property that is energy is done on the machine code. But anyway, having said that, we go back to the model, and the next step is incremental analysis. So incremental analysis is, the change, as you can see here, is that now we have several versions of the code. We have version 1, version 2, version 3, and as we change versions, we take snapshots of these program sources. This can be at each pause while editing, each save, each commit. For example, in the integration system and the continuous integration system. And these differences, these increments of constraint horn clauses, it doesn't matter, the source language doesn't matter. In the end, it's expressed in an incremental change in the horn clauses, are detected with respect to, with the previous snapshot, and then we reanalyze. We annotate and remove potentially outdated information. We reanalyze incrementally only the parts needed, module by module, until an intermodular fixed point is reached again. And then we recheck and optimize. To see a bit how this looks, this is a real analysis graph from a small application that has a planner. It has 3 modules, a planner, a small user interface module, and it uses a library, which is not too much of a library, as you can see, but it's some part of our library. And now let's assume that there's some change here, that there's been some additions to the library, and there's some deletions in the planner, in the main program. We have added something here, and we have deleted something there. Now, for example, we concentrate on module, and we see that there was an addition, so there's some computation here, so we add some part of the graph, and this creates new call patterns back into the planner, new returns, new exits, which in turn produce new call patterns there. And then the deletion eliminates part of the graph, trying to eliminate a minimal part of the graph, and then recomputes after that elimination, and maybe creates other new parts of the graph that are generated after that elimination. As I said, the algorithm maintains local and global graphs with call success pairs. These should be really tables, local and global tables with call success pairs for the predicates under dependencies. So we have the local tables in each module, and then we have the tables at the interfaces, which is how the modules communicate. And this is incrementally with additions, deletions, and the idea, of course, is to localize the fixed point as much as possible inside the modules to minimize the context swaps. All right, so we have some results here, but I will, just summarize them for the sake of the talk. In just saying that, the process, the modular incremental process has guarantees. It will provide a correct approximation, so it's correct, so a correct over approximation of the semantics, even if we're using widening. But if we want to get the exact same least fixed point that we get if we analyze just one module without incrementality, we do have some conditions on the widening. The idea is that if you, this is something that other people have also realized later, that if you have a widening, because the widening is kind of a bit arbitrary, right? It will depend on the order in which you process the modules will affect the order in which you apply the widening, and therefore you can get other more general results. Always correct, but maybe not the least fixed point. So you have to put some conditions on the widening which are in the paper to get this to work. I mean, if you're interested in getting the exact same least fixed point, which you may not. I mean, anyway, and then we have we got some pretty interesting results also for reanalyzing starting from a partial analysis. You have an analysis that has stopped without being completed and you want to restart it after changes, that it also works. The algorithm also works for that, which is very useful if, for example, you're editing and you're changing things while you're editing and it hasn't quite finished the analysis yet, so it can resume from partial analysis situations. Some experimental results, I'll just give an idea because it's better to just go through some examples. So the speed up is really unbounded, the speed up of, if you do modular analysis, you can have 1 million modules and only make a small change, so you can just make it, depending on the benchmark. But for a set of benchmarks, we were seeing order of magnitude speed up of incrementality with respect to not being incremental, and modular incremental getting even more speed up, about twice or so with respect to non-modular. And also, we managed to accelerate modular analysis from scratch, but that's really a detail. All right, so we saw verification, we saw incremental verification, incremental analysis, incremental verification. So the next step for our system, of course, is to add the interactivity. This is more engineering, than science, but it's it's fun. So the idea is that we add in the integrated development environment some support for communicating with the analyzer. So the idea is that the IDE can calculate easily. So we normally in the incremental analysis we calculate the differences inside the analyzer, but the IDE can also very efficiently calculate difference, because it's editing the program. So maybe you get that. Sometimes we get the difference directly from the IDE, from the editor, or the environment, the development environment, and that is what's fed here. And of course, the idea is that whatever results you get, be it for the compile time checking or even from the runtime checking, are reflected back on the source program in the IDE, which is something that we have done for a while, for like syntax errors and so on. But the idea here is to elevate it to a different level. We have made an interface with Emacs by extending flight check, which is what most of us use. We also have a browser version that I'll try to show, where everything is running inside the browser via compilation to WASM. With a VeriFly. VeriFly is the name we've given. It's a funny name, no? It's a VeriFly, verifying on the fly. So it's a verification on the fly, the VeriFly system, or the VeriFly approach. But you can do it for any IDE. For example, we have a version now also for Visual Studio Code. All right, and so I think with this, I can maybe do a little bit of demo, show some things, hopefully fun. So some very basic stuff first, for those that have not seen this system before. I'm going to basically take this out, and I have here, this is just plain Prolog. I have a predicate that defines 3 colors, red, green, and blue. Of course, if I load this predicate, let me do it in a different way that is better. Load it like this. There. And I call color, I mean, it's Prolog, right? So, I get red, green, blue. Now, this looks awfully like a type, right? So, in Chow, this can be a type. The only thing needs to be a type is to be declared that it's a type. Actually, a type is just a special kind of prop. So, in general, props are things that you can use in assertions that I will be able later to use in an assertion, like here. I can use color here in an assertion. So, if I declare something as a prop, then it's something that I can use in an assertion. It has to meet certain conditions so that it can be used as a runtime test and also so that the analyzer can understand it. And then a particular case of prop is a reg type, a regular type, which I can write because I loaded the reg types library, and I could write prop because I loaded the assertions library. All right, so now nothing has changed. You know, if I do this, I'm still, you know, I do that. And then the cool thing is that now I have this predicate, you know, which of course is predicate that returns red, no? That's obvious. And if I just comment this out, then the system on the fly, hopefully, if it wants to do it, let me put it here on top. Okay. Start again. Okay, I know. Okay. Okay. It's giving me the error there, but I mean there. So it just said that it has verified the assertion, the QX assertion. So basically, it's taking this as a property, and I'm here. What I'm saying is that predicate Q of X, when it exits, X will have the property color, and that gets checked statically, as you saw. Now I can do a little bit nicer, and I'm going to, because I loaded the functional syntax library, I can write predicates like this. So when I put colon equals, that means that let me just do something real quick. If I have P of AB, I can also, in the functional syntax, I can write also this like this. These two things are exactly the same thing. So it's just syntactic sugar to write in functional syntax. You know, so I take the last argument and I make it special and I mark it behind the equal dash. So it's the only thing. But that allows me to write this like that. Right, and then write this. Whoops. Like that. Which of course still works because it's exactly the same program as before. It's exactly the same thing, no? And then I have more syntactic sugar. I can do this. This is an OR. And now I get a nice type-looking thing. Eh?
So in order to be declared as a function, you do not need it to be a function.
No. No, in fact, you see.
It's a non-deterministic function.
Exactly. It's just syntactic sugar, and we love it like that. What we like is the syntax, not the semantics. The semantics you can have, but it's very simple. You put an assertion. You want a function? Okay, so you put an assertion. You say that all the inputs are ground, the last argument is a variable, and it's deterministic. And now you have a function. In fact, we have a macro func that does that, but it's on top. To be a real function is a restriction on top of predicates. Yep. So you see, this is still working. You know, and it's still verifying. No. See, it says here it has checked the success of Q. Okay, so now, just for fun. I mean, we're here to have fun. So this is a bit more interesting. So color list, of course, this is, let me write it first, and then we'll do parametric and everything, okay. So if I can do color list like that, I'm first going to write it in Prolog. So color list would be something like this. It's either nil or X, head, tail, right? Where H is a color, right? And T is a color list, right? So this is my color list. Of course, if I run it, I can check if something is a color list. So this is very important that you can run your properties because they have to be runtime tests because they may be undecidable. It all has to match. Okay, and then of course we have this very nice thing that we can explore types. Now, of course, we look at like this and it looks a bit ugly, the numeration, because of course we do it in depth first. Easy to fix. Well, before I fix that, let me just fix the syntax. I can, of course, I'll do the functional transformation like that because it's kind of fun to do. So I do this. So that was just using the extra. I still keep the where. I can still write a where. So that's still the same program. And then, of course, this H is actually the output of color, right? So I write that like this. I just put here color, but it's not the constant color, it's the output of color. Okay, and then I take color list and I put it here. And of course, it's not the constant color list, it's the output of colored list. All right, and then I look at that and I go, oh, that I can, the head is the same, so I can write I can put only one head and write it as a disjunction. And I have my type declaration, right? And then but the great thing is that I can run it. I can explore the inhabitants of my type. And then if I don't like that enumeration, great. So that's why we have our libraries. We can go to the search rule library and say, run everything breadth first. And then this gets much nicer, no? And then you can use your types as property generators, as test case generators, and then you don't have to invent property-based testing, which is, you don't have to invent many things.
You have, let's say, a random.
We have random, we have iterative deepening, we have all that stuff, yes. Yeah. We have random, we have iterative deepening, you can vary the parameters, and of course it's a world, what you can invent, but it's not so much, we use this stuff, no, and it can be, but it's what I'm trying to transmit is more the concept, how simple it is if you do it right, how many concepts you can incorporate in a, very simple language, it's all Prolog. It's all Prolog with a little bit of syntax and Chow Prolog is very good at being able to define syntax and add syntax, and all these little things are expansions, but they're modular and it's really easy to do. So these are just let's say user level extensions, all the ones that you see here. Okay, so far so good. And what else? So I did the color list. So I can say, for example, this predicate. I don't know why today it wants to put the messages 2 lines up, but who knows. So for example, that is verified also, as you can see. So it's telling me color list, that it is X is the success, the success of M is a color list, which is fine. And if I put something else, and of course this is all running in the background, it's doing the incremental, it's doing, all these things, no? And then if I do that, then of course this is not a color list anymore, right? So I can also hover if I want there. So you see, it tells me false assertion because actually, you see, it's the type red A, but that's incompatible with color list and so on, and it has done that. So this is, with abstract interpretation, there's no types, no. It's all abstract interpretation. It's just a shape domain and the E-terms abstract domain doing that. All right, so if I go back to green, for example, so everything is ducky again, and we get our assertions proved. All right, and then of course we can have more complicated. Now we can have sorted, for example, which I'm writing like this, and then interesting. We get a warning here, and the warning. If I hover here. Is telling me that it could not verify the assertion because it cannot guarantee that when you call this this property, this, which is a Prolog built-in, is going to be called properly. So it's warning you. You might call this with a variable, and then, of course, if I call sorted, like this, it says yes, or if I do like that. It says no, fine. But if I call it like this, there it gives an error because it's calling x greater or equals than y. Now, of course, what I want there is not the Prolog built-in. What I want there is for example, well, first it doesn't know anything about that. It's telling me that it's illegal, the predicate undefined in source. But I can maybe add CLPQ, why not? And then everything is ducky again, and then I can, things get much nicer, of course, no? All right, let me just do this so I don't forget. And now the last thing I want to show with this example, which is it's very small, it's very simple, but it's doing a lot of things. I hope you see that. Okay, so I put prop sorted because this is not really a regular type. It's maybe a dependent type or something. I don't know how to call it, but it's a property. We don't give so many names to things. They're just properties. Then, for example, if I call P that calls Q, then I get an error. And this error tells me false assertion because, and it says, well, how can it figure out that sorted that is not sorted? Well, it's not figuring out it's not sorted. What it's figuring out is that sorted implies list and that Q is returning red. I don't know if you remember that, but Q is returning a color. And then, of course, red is incompatible with list. Now, how do we do that? We do that because we analyze the properties themselves with other domains. So if you analyze the property sorted with domains of regular types, then you know what type it implies. So the success set is over-approximated by that type. And then if you compare it in the right way, you can prove that, that sorted is false. You cannot prove that sorted is true. For that, you would need a runtime test or a more powerful domain. Daniel has developed a domain that can prove sorted. But I'm not going to do that now. All right, so this is so much for this example. Let me go to another example. So yeah, a bit more evolving to a bit bigger programs. So for example, if I have this, sorry, it should be like this. Okay, so if I have this quicksort program, if I go to the beginning, it actually tells me a summary, no? And I know that in this module, in this program, I have two. So I have the number of assertions that went to checked, so that were verified, the ones that went to false, remember the picture, the ones that are in check. So here I have two in check. I can see them here. They're right there. This one, okay, and this one. And what it's saying is that it cannot verify that when you call arithmetic, it has the right properties, which are oops, yeah, okay, I should. So the right property is, one thing is that if you point with the pointer, the tooltip disappears. So the property is, it cannot prove that when you call equals less than, it's an arithmetic expression, what you see on the top. So it should be an arithmetic expression. Now, how can we fix this? How can we fix this? Well, one thing is to use this module in another program, and then the other program will call it in a particular way, and we will infer if it's called properly. But if we want to, verify it on its own, then we can add an interface declaration. Now, none of this is compulsory. This is the important part. These are all voluntary. So I add an interface and I say that quicksort, when you call quicksort, the normal way to call it is to call it with a list of numbers and a variable in the first argument and a variable in the second argument. And then, this, at literal one, I successfully check this assertion. So I'm proving, remember that the arith expression part, that when you call these A and B, which are X and F, are arithmetic expressions. And the same here, no? I think I don't even need this probably. Yep, exactly. So that's sufficient. Now I can do a lot more than that. I can do for example, here I have added a lot of things. I said that. So what am I saying here about quicksort? I'm saying that if you call it with a list of numbers, it will return a list of numbers. It will not fail, and it will be deterministic. So no matter how you call it, provided it's a list of numbers, it will always succeed, and it will never give you two answers. I mean, it will give you only one answer, so it's deterministic, which is more or less exactly what a programmer wants of their programs, to catch errors and so on. And we're catching this. What have I done here? There. Oh, because I erased it. There. So if I see here, it's telling me that it's verified. This assertion is verified. Verified assertion, blah, 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 blah. And anyway, so if I, here's maybe more interesting, I have other things. So all these assertions There you are. So all these assertions are verified. You see, these carets here mean that the assertion is verified. Doesn't give you a lot of noise if the assertion is verified. You know, we can play a little bit with this program. For example, if I take out these equals, I immediately get a problem. What is the problem? Who knows? What is the problem if I do that? Can fail, right? Exactly. You know, so I get here. If I look, it says it possibly fails. You see there, the NF, the non-failure analysis is saying. So this, by the way, these are the different domains. So the different domains, this domain says that, this domain says that, this domain says that. You can have gazillion domains, and depending on the properties, it uses some domains or others. So it says it possibly fails. So I cannot prove that it doesn't fail. Equally, for example, I can do this, and then I again get a problem, and now it's the opposite problem, is that it's not deterministic anymore, right? So that's very useful. Where else? And of course, I mean, there's all kinds of other, oh wait, so no. Still giving me a problem because I messed up. There you are. Okay. Are you getting better? Yes. All right. Oh, and of course you can do the usual things, you know, that if you like mistype something, all hell breaks loose, no? Because you start getting all kinds of things that don't match in different places. So the argument is that this makes Prolog very as useful as before for prototyping, but then when you want to coalesce it and make it reliable, you know, you can do it, and you can get the same kind of reliability, and with properties that are hard, you know, that they're complicated. All right, more things. You can control the analyzer. There's this option menu, and you can do all kinds of things. You know, one of them, for example, that's interesting, is to turn on program point info. So I did this. This is turned on, and many other things. No, but if I analyze the program, and I'm doing it now in a different way, and I look at the output, I get all kinds of information. So I get the true assertions. The checked assertions are the things that have been checked. So for example, this one, just ignore it. It's because of the entry point. But like this one, for example, says that it's a computation assertion that says if you call it with a Liston number, it doesn't fail and it's deterministic. That has been checked. So basically, our pred assertions here, these pred assertions have been translated into comp assertions and all kinds of assertions. All these other assertions, the true ones, are the ones that give the results of the analyzer. And the interesting point, perhaps, is this, that we also get information on program points. So if you see here, you have a clause, a quicksort clause, and then all these trues are the information at that program point from the analyzer, from the different domains. So for example, here we know just before partition, for example, we know that first and rest will be ground, and so on. Or here before, more interestingly, perhaps here before the greater or equals, where are we? There. So before this, for example, before this less or equal, we have lots of information, but one of them is, for example, that X is a number and that F is a number, and that's what allows us to, you know, prove that there's no problems, you know, because we have all this information, and we have versions and so on. Okay, let me speed up because otherwise I won't finish that line. So I'll go a little bit faster now because I want to go slow so that it's all very clear. So more stuff that is kind of neat. So we also have these things called modes, which, you know, if you're a Prolog programmer, you'll be familiar, but modes are just macros. So they are macros for assertions. So if we look at our previous this is pretty much saying the same thing. So this assertion, this assertion here and this is just a compact way of writing the same thing. So the modes basically are macros of properties, and they're defined like that. There's a language for defining modes. Say, well, my plus means that it will be non-var on calls and whatever, or var on calls and ground on exit. You can define your own modes. So there's a library of modes. And they also have other compact, these are like Mercury style determinacy, and these also get checked on the fly. As you can see, the little carets, so that works. Furthermore, since some people don't like assertions and they don't want their program to have some extra syntax, some directives, they don't want that. Well, we can do other things. We can do. We can put the assertions inside doc comments, inside machine readable comments. So that is again the same. So you can say. This comment, which any Prolog, so this program, any Prolog program will read, and then the assertion is in a comment, so it doesn't bother, you're not adding any syntax or anything, so that also works. So, okay. And so you see the little carets appearing here. More things. Quick things for this example. Also, I have to save, so it runs. So it gives me an error here. Now this is naive reverse, written with the functional syntax, but this is the naive reverse in Prolog that runs backwards and everything. But I'm saying that if you call it with a ground list in A and a variable, so you run it forwards, we will get a list in the second argument. A and B will be independent. We put that just for fun and so on. But that it doesn't fail, that is deterministic, that it terminates, but we also said, I don't know how I did that. Wait, I'll do it again. Okay. We're also saying that it's linear, and of course it doesn't like that at all, and it says there. So it's showing that naive reverse is not linear, it's quadratic, so it's giving me a cost error, which is, so that's to show that it's not just types, it's not just, types are just one approximation. I can fix that, of course. I can say, and then it gets, it verifies. So nice. And I can do other things. Like for example, if I can see here that this is an upper bound, the length of A actually is not an upper bound, and I can even look, why is it not an upper bound? So I check, and it says, it's +1, because the base case, it's counting the base case. So it's telling you, no, it's the upper bound is A +1, length A +1. Okay, let's see, +1. Now. But okay, I like it like that, so I put O. Okay. I hope I get some smiles from you. All right, so a bit more complicated program. I'm going to run a little bit because I'm running out of time now. We started a couple minutes late, no? So, yeah. So, okay. So this is a bigger program. There's a parallelizer, and then we get, lots of checks. Anyway, so it's basically the same thing. If you look here, for example, here annotations is reasoning about the data structures that are being built. It's basically processing programs and parallelizing them and so on. And here, basically, we're realizing that when it gets here, we're saying when you get here, phrase should be a variable. Info and phrase should be independent, should not have pointers. They're recursive data structures, but they don't have pointers. Phrase would be, info would be a recursive data structure that doesn't have pointers. And on output, the both will be ground. And this, as you can see, is checked. And anyway, so this is a more serious program. But I won't spend time for that because I want to show something different. Yes, so one of the cute things is that this all runs on the browser. So, the whole ChowPP system runs on the browser. And if we, what was I going to say? Yeah, let's just do the quick sort. I have a bunch of examples here. The same quick sort that we were doing. Yes, so we can, since we're familiar with this, we can load this in the playground. So this is the Chow playground. So here you can, of course, load this program and then basically do quick sort. No, it does work. No. Now the cute thing about this implementation. We've done several implementations of these kinds. What is it? 3, 2. It's going to be backwards now. So this runs here just the same as in the. But the thing is that here everything is running in the browser. So the whole shell system has come down, the analyzer, everything has come down, and it's running in the browser compiled to WASM. So you don't need any installation or anything to run this. And you can also analyze and check the assertions, as you see. So we get all the output, the checked, and so on. And here's saying that the successfully checked assertions and so on. And if we mess up something, like, I don't know, we put here num to say something. I didn't turn on, sorry. I didn't turn on the flight check mode. Okay. So if I do that, hopefully it works. No, list num. Yeah, so that was the, yeah, it's giving me an error. And the error is that, that is not a number. No, but if I go back to list num, why? List num, yeah. It wants to go there. There we go. Now, so this should get fixed. If I'm syntax error, I'm asleep. List, list. Yes, sorry, I'm asleep. You guys are asleep also because you didn't help me fix it. Okay, and now why is it list? No. This num, why I'm still missing a parenthesis. You guys should, yes, now, yes. I'm asleep, I'm completely asleep.
After there's a parenthesis.
After what?
No, after no, is this no, comma, X.
Well, that's, yeah, but this is why, no? So why is it telling me? Well, I'm too stupid to fix it, but believe me that it works. What am I doing wrong?
Is short.
Huh?
Parenthesis, this, parenthesis, no, comma, delete this parenthesis.
Ah, yes, so this one is wrong also. So I messed up this one also. You're right, yes, on below the same, yes. I was too asleep, yeah. Okay, yeah, you see it works, It's not a demo, it's the real thing. Okay, so you see that it works on the fly also on the, okay. Now, last thing, so this is the last cool thing, is we also have, because we can run the analyzer and the verifier and everything, we can embed these examples. So you see, as you saw that we can actually run the analyzer by hitting that, and we can load it in the here on the fly. But for example, we can generate tutorials like this one. For example, this is a tutorial of Prolog tutorials, but also Prolog analysis tutorials. So this is, for example, a tutorial. I'm just going to go to an example here. Right, so here we explain the determinism domain and so on. And then we have this sorted insert program. And if I hit there, this analyzes, and then I can see that it says possibly not mutually exclusive, multi, so this is not deterministic, and maybe I want it to be deterministic, this sorted insert, since I'm calling it forwards and so on. So I'm basically missing a cut here. And then if I reanalyze, you see now it's detected that it's deterministic. But this is running in the document. The whole analyzer is inside the document. That's pretty cool. So if I reload it, you see it goes back to the previous thing, no? Because it's all inside. Anyway, so that was the last thing. A couple of final remarks. Summary. We achieved what we wanted to achieve. Hopefully, we're still always improving, of course. Plus, we made Chow Prolog even better. There's a lot of people involved in doing this. Many or some are here, and there's also a lot of people that worked previously on the system. So it's a totally incomplete list of where you have also John and so on. And anyway, so thanks for now.
very much, Manuel. We've time for a bit of discussion, questions. I saw Mikael first.
Yeah, so thanks for the interesting talk. So it's quite impressive what you have done, and I'm still do not know what are your, or whether you have any boundaries. For instance, I have a question. So if you have data structures and have predicates inside the data structures like search trees, and you want to prove properties of if you have red-black trees and do operation on this, could you also cover this as properties?
So trees, we can cover trees, but if you have, you mean if you have properties inside the trees?
Inside the trees, for instance, that
well,
they have, that should be balanced and so on, and these kind of properties.
Okay, so let's, so you can write the property, of course. The property can be written. What is a tree with certain characteristics of the nodes or whatever. Let's say a tree that all the nodes are greater than 3. Let's say that, no? So you can write it in Prolog, of course, and then you can use it as a runtime test. So you could use it in assertions. You can always write a runtime test and use in assertions as a runtime test and put test cases and so on. Because the nice thing about the system, it unifies unit testing, test cases, property-based testing, static testing, and so on. Then the next question, so you can write the property for sure, and you can test it at runtime. Can we infer it at compile time? Well, that depends on what abstract domain we have. So for example, if we have trees whose element has sizes, that we can do because we have a size types domain that we use for the Pedro came up with we use it for the cost analysis, because we need to know the sizes of the things inside data structures. So those we can do. Can we do more complicated things? You have to develop an abstract domain, and that's why Daniel gave the talk yesterday here in Lobster about designing abstract domains, because in the end, I mean, if you have a complex property and you want to prove it, you have to work. You have to work. You have to have, somebody must have written a domain, you or somebody else has written a domain that is capable of, the theory is capable of it. The question is, has anybody sat down and written the domain? It's still, the advantage is that you write the domain. So of course, what's that we have? Testing. Testing we can do, no problem. They're improving is they're improving, but you have to do it by hand. You have to work at it by hand. We're trying to find the automated point in the middle, the farthest we can go with total automation. So there's a price to pay, which is to develop domains. So that's it.
Thanks for a really cool talk. So in the data log for static analysis world, people are trying to make things incremental by making the whole data log engine incremental. How specific is your incrementality here to the analyzer part, or could it also be applied like to the whole Prolog program in general?
To the execution of the Prolog program, no, I don't think so. I mean, it could be done, but it doesn't work right now. But the analyzer can be used. I mean, the analyzer is, in reality, the analyzer is a Prolog system. It's a Prolog system with tabulation. So you can actually run the programs in the analyzer. So in that sense, yes. In that sense, you would have a super optimized with tabulation. We also have tabling in the Prolog. So the tabling you can do. I don't know, Jose maybe has a better answer.
You answered.
Oh, sorry.
I think there are some papers from XSV guys,
Yep.
Prolog about tabling incremental.
Oh, yeah.
Yeah.
So the XSV Prolog system that implements tabling, they have some papers about the incremental tabling that connects, as Manuel said, with the fixed point, because our fixed point is a tabling.
It's an OLDT,
strategy,
so it's a tabling resolution prover. So in fact, I mean, it's the exact same algorithm. We discovered this. We published the algorithm, the incremental algorithm for the analyzer and for the XSV system in the same conference, in the same SAS, if I remember well. So we came up with it. I think we came up with it a bit earlier, but yeah.
Other comments? Yeah.
Okay, you say that, well, this is for Prolog, what you showed us, but it can be applied to other languages via translation from the language to constraint on clauses. So
Yes.
I was wondering, first, if there are, let's say, realistic languages that get translated to constraint on clauses, and for runtime checking, can you do something? I mean, you get, let's say, the verification through constraint on clauses, and then the residual checks are done at runtime in the language, in the source language,
Correct.
or something like that.
Yes,
I don't
yes.
know. Is that possible? Can you do that?
Yes, yes, a very, very good question. So let's analyze the parts. I mean, so you can take the original language. I mean, actually, that's why I put this example here. No? So you can take the original program. This gets translated into machine code, LLVM. Then we translate the LLVM to horn clauses, analyze the horn clauses, and we reflect the results back on the source program here. Now, we haven't done, so we've done that for Java bytecode contracts, for Tezos contracts, for Michelson. We have done it for XC, for machine code out of C programs. These are prototypes. They're not production systems. The production system is pretty much a production system nowadays. These other are prototypes to show feasibility. Now, we have done this part of injecting the results back on the source code. We haven't done the on the fly, but it's engineering. I mean, it can be done, no? Now, the interesting question, but you went further, and it's a very interesting question, which is, now, if I write the properties in my source language in C, let's say, I run an assert in C, then I can, of course, I can do all these tricks of analyzing that, because I can translate the assert to, if I know how to translate Prolog to horn clauses, I can translate the runtime assertions, the ones that run. Those I can translate to properties and to horn clauses and use them in verification and so on. So I think some part of it could be done. What is harder is if you write a property in, let's say, for example, terminates or cost, you have to write the runtime checker. You have to write it in C. But we also have to write it in Prolog, right? Because we don't have, it's not like you write some magic bit of Prolog. No. I mean, for example, for the terminacy, you know, that's a check that is built in, because we basically look at, the efficient way to do is to look at the choice points in the stack, in the choice stack and so on. So partly. Great question. Yeah.
Yeah, one last question then.
Thanks for the exciting talk, Manuel. So just kind of building on the last question, right? Like, if I'm trying to design an analyzer for a new language, complicated language, JavaScript or so forth, then I need to build that translation from JavaScript to constraint horn clauses, and that's a lot of the challenge of sort of encoding the semantics. So I don't know, how hard is that, and is there some sort of gradual development process that could allow me to sort of prototype more quickly kind of analyzers for new languages?
Okay, so we didn't get into how you do it. You could ask John, who's the master on this. I mean, so there's several ways to do it. There's one standard mechanical way, proposed by John, is to you write an interpreter, and you do the Futamura projection thing. So you write in horn clauses an interpreter of the language, and then partially evaluate the program. So that's the cool and right way to do it, because you're sure it's correct. The translation is correct. Then there's, okay, so you do the Futamura projection by hand and basically have a translator, based on what you see from your interpreter. Because in the end, you eliminating the interpretation loop, you can also do it by hand if it's too hard. Although John has had great successes in doing that automatically. But then, and there's the whole thing about the small step and big step, and I mean, we'll get into a humongous area here. But I should say that the way that we do it, because a lot of people do the small step thing, we is to, to kind of describe transitions in the states of the imperative program. But we basically use the fact that Prolog can run imperative programs. So basically, we translate the imperative programs to Prolog. So we use, that's a bit harder to understand, but basically, if you have an analyzer of Prolog, you can analyze any program. It's not, there's nothing that Prolog doesn't do. It has assignment also, you have to deal with it, and it has dynamic modification of the programs. If you have a dynamic language like JavaScript, you're not any worse off than in Prolog, because Prolog has a certain retag and can change the program on the fly, and we have to deal with all that. So it's as complicated as it gets. This is why we have always worked with Prolog, because we think it's kind of a superset of what you can possibly do in a language. You know, it has all the complications. It has pointers, which normally you don't have in functional programmers and so on. It has logical variables, which are pointers, and they can have aliasing, so you have aliasing analysis and sharing analysis. You have everything, all the complications that you think. If you can do it for Prolog, then you just translate and analyze. That's at least our theory, no?
I could just add that you can use the compiler also. I mean, you translate from the intermediate representation generated by the compiler. So a lot of the work of handling the source code could be done by the compiler, and then you translate the control flow graph or something and into horn clauses. But it's a long story.
It's a long story. So LLVM, you know, like I said, this was done that way. This was done with the LLVM compiler. So you take the LLVM representation, and that's what you translate into the horn clauses.
Let's take the discussion offline from now on. And
right. We have another
Manuel,
talk, yes.
and for a very interesting and stimulating talk. Thank you.
Thank you.
Right. Let me just get the details for the next talk. So while we're setting up, I can introduce Maria Kulasch. Is that more or less the correct pronunciation? From the VII Universität in Hagen, in Germany, who is going to give a talk entitled A Term Matching Algorithm and Substitution Generality.
And in particular, generality of the question of generality of substitutions. And I present a decision procedure for this. So when we have substitutions will be taken in the traditional view, and that is modeling substitutions as total mathematical functions, and being composed as any other functions. So that straightforward modeling has been put into some doubt in the 1990s when some examples of non-intuitive behavior appeared, and in particular in the question of generality of substitutions. So as an example, if we have a substitution replacing the variable x with the variable y, should it be considered more general than substituting x for a constant a? So intuitively, of course, we are just swapping one variable for another, so why shouldn't that be the same? But formally, the problem is the accepted definition of substitution generality is a bit tricky. So for sigma to be more general than theta, we require that there be a mediating substitution delta, which composed with sigma gives a theta. Observe that I'm using the old order of application, so the substitutions will be applied from right to left, not in the meanwhile prevailing post-fixed way. So if we accept this definition of generality, and so far as I'm aware, there is no other, then this substitution is not going to be more general, right? In case that the meta variables x and y here point to different object variables. Some will be using only meta level in this talk, so no reference to object variables. So in that case, the generality will not hold as we would have expected. So how do we know this? We surely cannot try all substitutions for their being eligible to be this delta, but we can prove something. So assuming we have found such a delta and compose it with x to y, well, in order to obtain as a result x to a, to the constant a, we would have to connect this y with y to a in delta. So in case y and x point to different things, we would have two bindings in our result instead of only one. So that's the reason. And well, however nice such custom-made proofs may be, I was wanting mechanization of this, so a decision procedure. And observe, we are speaking when well, more general or equally general, right? Because at least a general would be a mouthful, right? So method and results, matching of substitutions, we reduce to matching of terms, which is easier. For term matching, we provide a simple algorithm called T-mat. It was originally from a textbook of on the term rewriting called Therese in a non-deterministic form. And we made it one pass by accumulating the bindings using a more general representation of substitutions that we are suggesting called the relaxed form. So that's about method and results. And now a bit terminology, generality of terms and generality of substitutions I've put on one slide to show the similarities and how far they actually go. Observe that I'm not using the same symbol for both, and I would be advising against such thing because they're not really analog, because in case of terms, we are applying this mediated substitution on the more general object, but in case of in case of terms, but in case of substitutions, we are composing it with the more general objects, and that's not the same. So the other part of terminology is relaxed co-representation. Well, normally substitutions are represented in a very restrictive way. only non-fixed points are taken into account, and there must be only finitely many. So the whole rest, the infinitely many, are just being ignored. They are mapped to themselves, right? But that is not sufficient for all purposes. For example, if we have a term S which can be mapped to a term T, but we also want to account for all variables in S. So bookkeeping of variables, then we have to tolerate also that which I called, on lacking a better word, passive bindings. X goes to X, so nothing is changed, right? That must be tolerated. So a definition would be that a relaxed core for a substitution is any finite variable pure superset of its core. I'm not talking about domain. That's another source of confusion. Every substitution is defined on all terms, right? So it's core in my, well, vocabulary. So obviously that's not unique, but for any application, we have a fixed relaxed cost. And for a symbol, I'm using just D instead of DOM for core. Well, the main purpose why this relaxed form is being suggested is that placeholding which is enabled by relaxed form is vital importance when we build a substitution and the variable has been confirmed to be passive. Well, it is passive, but it is not free, so it may not be bound at some later point, something else. So looking about that, it's a bit surprising that relaxed form hasn't been introduced much earlier, because it is implicitly used like forever, because when we compose substitutions, like in this animation, wow, he's doing everything at once. Wow. Sorry about that. That's out of my control. For some reason, it's the animation. Well, I kind of cannot. Well, let's try this. Skip the animation, right? Wow. And again, further. Well, but you've seen it, I suppose. So the variable x start at first was deactivated. It's no longer active, but it's keeping this place. So the binding x to y must be discarded. So it is passive, but it's not free. So that's the idea. And now to the promised algorithm, term matching or subsumption is the most basic kind of pattern matching, just purely symbolic. And the difference to unification is that a non-variable may not match variables, right? So if you look at the definition, it's generality, right? So a term matches or subsume another one if it's more general. And the algorithm for term matching that I have been adapted a bit takes apart from the arguments from the two terms L and R for the purported more general and less general term, also an accumulator. That's a substitution in relaxed form, and output will be a possible match if the algorithm does not fail, a possible matcher of L and R that is extending the accumulated delta. So it has 4 rules. If L is a variable, and there is already some binding in the accumulator, but to something which is not the intended R, then we have divergence. We are trying to bind a variable to two different terms. Otherwise, we put it in the accumulator. Then a failure, if, well, the other three rules are handling the case of L not being a variable. If L is not a variable, but R is, we have shrinkage failure because we are trying sort of to shrink a non-variable back into a variable, which is not possible with a mathematical function. The next failure is clash because if you have non-variables but with different outlines, outline, well, it's the top level functor and the number of arguments, so predicate indicator is a standard. And the last rule handles two terms with the same outline, so we need to iterate the algorithm and update the accumulator as expected. Justification of this algorithm would be in two parts. If it stops with failure, there is no match of L and R extending delta. And it is based on two observations. If a function maps L to R, then it maps each subterm occurrence from L to a sibling in R. Well, in my paper, I've put a compact visual definition of what it is, a subterm occurrence, and what it is to be a sibling. Basically, a pair of corresponding terms in corresponding subterm occurrences in two terms. The second observation, each time the mat is re-invoked and its arguments L and R, that should be dashes, because that need not be the same as at the beginning. Denote a pair of siblings within the original term, so that justifies the first part. And the second part, well, the algorithm obviously always terminating, and if not with failure, then it produces substitution, which is a match of L and R extending the accumulated delta. Well, in the paper, I've put additive to delta. It's also correct, but it's an understatement because it's already added. It's already there. Right? That can be seen by structural induction, which is the native method for terms. So, in addition, if we call this algorithm with the identical substitution, with the empty substitution, then the resulting match, its relaxed co is exactly the set of variables in the term L. So we say it's L focus, it's exactly the set of variables, and it's relevant for L. It's a notion by app, meaning no extraneous variables, only just that it's there. Well, perhaps the only case where we don't need an algorithm or proof to be sure that generality holds is if the left-hand term is well, empty or identical substitution, then it's obvious according to definition. But what can we do in other cases? For example, substitution x to y compared to its extension x to y and y to x. Which one is more general? Is there an opinion on this? X to y or x to y and y to x, back again, right? Please? The second one. Well, I would advocate, you're right. Well, renamings are always the most general, so that, yes, so that's the answer, and we will see later that it is also confirmed by the decision procedure. When I started with this, I thought it would be easier to try with refutation. So can we have a term, say W, which is a witness of non-generality? So a term such that if there can be no substitution, no mediated substitution delta, then it will become apparent from the instances of W by sigma and theta. And luckily, it's just simple. We just take all the active variables of sigma and theta, and that suffices. So we apply a term matching algorithm, for example, TMAT, on the respective instances. And well, if we get an impasse, then there is no the generality is refuted. Otherwise, so here we have also this decision procedure. We have the other part. Otherwise, a matcher is found. So the generality is confirmed. In short, the method consists of reduction, so the problem of generality of substitution reduced to generality of certain terms. And also, if the matching succeeds with a substitution delta, then it is good enough for generality of substitutions as well. In practice, that would look like this. We put, for given substitutions, a triangular tableau. So in this case, the substitutions have active variables x and y, so that's what we have on top, the witness list. And on the slopes are the two substitutions respectively. So now we just have to fill in how they are mapping the witness term. In this case, sigma is producing y, and theta is producing ay. So the question is, can we match the left-hand term on the right-hand one? Can we? Well, it's not school, I know. We cannot, because y would have to be mapped into two different ways. Once but simultaneously, of course, right? Once it will be bound to A, and once it will be bound to itself, so that's not possible. There's divergence. And, well, that's a negative example. By the way, if you switch the order of substitutions, we don't gain much. Those two are incomparable. So, positive examples. Well, the first is above is an example by Ept. XY we now know is not more general, surprisingly, than XI, but it is more general than its extension. XA to Y and Y to A as well. And here the diagram commutes, so that means that we obtain a substitution delta which applied on the left-hand substitution produces the right-hand substitution. And the example below is, well, that we what we had as a question. The renaming on the left side is indeed more general than the other. Then it's, well, reduction on the right. And here we also see that the produced substitution is really in the relaxed form because it has one passive pair here. Well, in view of diminished interest in foundational aspects of logic programming, a question might appear, why is this important? Well, at least a referee of my paper put that question. So I can point to a famous counterexample which falsified the long-standing formulation of the completeness theory for SLD resolution. That's been around since 78, 80 in the work of Robert Hill and Keith Clark. It can be still accessed in Keith Clark's thesis. It's there, and it has been taken over in Lloyd's textbook. Well, the idea is that, well, it's put in the following way: every correct answer substitution must be more specific, well, an instance of a computed answer substitution. Well, it's disproved with the counterexample by hyping call, looking like this. We have this query and the program, and it can be seen that the only computed answer is x to f, y, z with distinct variables y, z. But a correct answer can also be x to f of AA. And as shown by hyping code, these two are not in the generality relation. It's also shown here with the witness term method that we also have here divergence, so it's not possible. The wording has been corrected, well, concerning Lloyd's textbook in 1993, there was a corrected printing on Springer Link. It's still there, this wording, but well, the correction went in the direction of using terms and not substitutions. So those answer substitutions are applied on the query, right? So now we have a easier problem, and also new concepts have been proposed, avoiding the need for substitutions when describing logic programming computations, or things like parallel composition to avoid the need for composition. Well, been into what I'm trying to point out here, substitution generality, not that analogous to term generality, so it must be perhaps revisited, the name or something, because moderated substitution is involved in both, and if generality goes both ways, so we have equigenerality, then the moderated substitution must be renamed. That's as far as the semblance goes, but visually, more general terms are, well, smaller as trees, but more general substitution can be either, can have a bigger course, can have smaller course. The case of bigger course we've just seen with the verify. And above all, the unfortunate choice of word instance when speaking about substitution, that's just not correct, because analogy to delta applied to a term S would be delta applied to substitution sigma, not delta composed with substitution sigma. But a substitution applied on another one is not always, of course, defined, and even if it is, the result is not the same as delta composed to a piece is missing, so that would be delta inverse on the end, that would be needed. So it's a problematic choice of a name. So my conclusions on the last slide, instead of ad hoc proof, substitution generality can be easily decided by term matching, reduce the term matching. New concepts like relaxed core, where fixed points are allowed, can help with bridging the gap between the traditional core representation and the meaning of substitution, which is defined everywhere, right? We cannot just ignore a big part of a function and accept that and expect that the rest will take care of all the needs and behave intuitively. So that's just the problem here, right? And well, as a last word, the terminology related to substitution should, in my opinion, be revisited. So words like generality, equivalence, instance, in talking about substitutions are a bit problematic and enriched. So that's all.
Thank you very much. Are there any questions? I have just one comment, really, because I remember a lot of controversy about substitutions and unifiers and the term lattice and so on in papers about logic programming in maybe 20 years ago, 30 years ago. And there was a lot of discussion about in the ISO standardization group for Prolog about the correct implementation of predicates like instance of, not only the implementation, but what should the correct results be. And in fact, there was a change made maybe 10 years ago to the definition of instance of in the Prolog ISO library. So maybe you should look at all those predicates in the term library of Prolog and check that they really are correct,
Wow.
because as you say, there are bugs in some of the foundational concepts of logic programming. So
That would be a tall order.
you should talk to Ulrich Neumerkel in Vienna about the Prolog standard for all these predicates to do with terms and substitutions. Any other comments? Well, let's thank Maria again. And just a few minutes late, but we'll start the next session at 11 o'clock after the coffee break.
Okay, so welcome to the second lobster session of today. We have 3 papers, 2 long papers and 1 short paper. The first one is about predicate anti-unification in constraint logic programming by Gonzague Yornaud and Wim van Hoof. And the presenter is Gonzague. Please, Gonzague.
Yeah, thank you. So hello everyone, I'm Gonzague, and in this work we've tried to define to come up with a first definition and formalization of what could be called predicate anti-unification. Anti-unification itself is well known. It's defined as the fact of computing most so-called most specific generalizations, or MSGs, of program objects. So the program objects can be terms, atoms, literals, goals, but it hasn't yet been defined for predicates and clauses. And an example of anti-unification is given here, where we have 2 atoms, and as you can see, the atoms share some common structure. There are some functors appearing in them, some terms that are the same, but some parts are different. And the result of anti-unifying these, which is in fact the dual operation of unification, is a new atom that's more general than the 2 input atoms. So as you can see here, we have a new atom, which introduces variables, and the variables, in fact, are what allows this new atom to be more general than both the input atoms. So for example, here I have an A in the first atom and a B in the second one, so I put a variable to show that there's some part here that's in fact different. So the generalization can be seen as a common template for the 2 input atoms. And the common uses of anti-unification are, for example, in inductive logic programming, where the whole goal is to learn new, more general rules starting from base facts. So you can anti-unify the facts and try to get some more general rule in this setting, but also in partial deduction, where it can be used to control some searches, in bug detection, code compression also, and the last example here, semantic clone detection, is the context that interests us, because we're leading some research in semantic clone detection in logic programs, and anti-unification, in fact, represents, by representing the common structure of different program objects, it can, in fact, represent also what's common between the atoms. So it can represent also, it's interesting because although it's a syntactic operation, it can represent some things at the semantic level too. The generality introduced is also a semantic one. So in practice, anti-unification has been well studied for ordered structures, such as terms. You know, the terms are ordered in the way that, in the sense that they are sequences. And in that particular setting, we have, for example, subsumption, which is well known, and which can be carried out in linear time. And then you have more complicated settings, for example, when you consider unordered groups or sets. For example, goals, when you consider the purely declarative logic programming, where the bodies of the clauses are composed of sets of literals rather than sequences of literals as in Prolog, then the problem directly becomes NP-hard, and it's a whole other story. Anti-unification techniques exist also for other structures, such as hedges, lambda functions, or even in functional programming for regular functions. But it does not yet exist for logical clauses and hence for predicates. And as I said before, it's necessary in our work, where in fact the clone detection process is steered by the fact that we consider the MSG, or the most specific generalization of two predicates, to be given, because thanks to this MSG, we can decide in our search process, we can decide how could we syntactically transform the input predicates so as to make the definitions closer to one another. And the generalization of both predicates actually has and harbors that specific information, but it hasn't yet been defined before. However, some related problems have been studied in the literature. Some have already tried to quantify the syntactic closeness of logic clauses and even whole inductive logic programming programs. Some others have tried to mimic analogical thinking, still in the context of inductive logic programming and machine learning, by using so-called higher order anti-unification, where you can also variabilize in the generalization process. You can also variabilize the predicate names, for example. And then even closer to our own work, some authors have studied the search for a blueprint of the algorithmic core of functions, which is not that far away from our own goal to detect semantic clones. And in that context, it's for functions, and of course we are more interested in the predicate side, but the idea stays the same. So anti-unification is known to be useful in fact, to have semantic applications. But as I said a few times before, we haven't got yet an algorithm for two input predicates to actually compute their anti-unification. So first, let us take a step back and consider the formalism which we'll be using here. And let us consider this example where we have two predicates, take and next sum. The first predicate, take, well, it computes simply in its third argument. A call to take succeeds when its third argument represents the first elements of the list in second argument. And the third argument is thus a sublist of the second argument, but restricted to the E, where E is the first parameter here, first elements. And as you can see, the body of the last clause here is, in fact, a set. So we have written the atoms, the literals, in a certain order, but in fact it doesn't, since we consider the fully declarative semantics, this does not, there is no real order here. And in fact, we also, as we're really interested in the theoretical results here, we also consider the different clauses to not be ordered. So a predicate definition is a set of clauses too. This will be important later on. And then you have the predicate next sum there, which computes in its last argument the negative sum, so simply minus and then the sum of the I first elements of its first argument. So although these two predicates, of course, they do different things. One of them extracts elements from a list, and the other one computes the sum, the negative sum of the first E elements of a list. There is some common functionality here, and that is the fact that we crawl through a list and we make an operation element after another, and we do these operations until for the first X elements here, E or I elements. So we would like our algorithm, our predicate anti-unification algorithm, to express this, to be able to compute a generalization of these two predicates that expresses the common functionality here. And as for syntax, we say that the predicates that allow to compare elements, numeric elements, are constraint predicates. So we have constraint literals that are built upon constraint predicates. And then we have user-defined predicates, in our example, take and nextsum, which are both recursive. And so we say that the literals built upon these user-defined predicates are atomic literals. But in fact, as you can see in the title, we've put constraints between brackets because here the fact that we use constraints or not is not really relevant. We're simply considering literals. So when we're speaking about literals, we're considering either atoms or constraints. Both are considered literals. And then we have, as usual, functors, which allow to build terms. So in our example, for example, E minus 1 is a term built on the functor minus, and the terms are used as the arguments of the literals. So, as I said before, anti-unification is well known for tree structures or sequences. So let us start by defining it formally. So given three terms or three literals, G1, G2, and G, we say that G is a common generalization of G1 and G2 if there exists two substitutions such that when I apply the first substitution on G, I get exactly G1, and when I apply the second substitution on G, I get exactly G2. So this is the usual definition of generalization and common generalization, and it's not unlike what we saw in the previous presentation with the generality of substitutions. And as usual, we consider a substitution to be a mapping from variable to terms. So here we have a quick example where we can see this term here, based on the functor f, has two variables, and it can be seen as a generalization of both the terms that are there below, because we can find the mapping from x and y onto 1 and h, and that's one substitution, but also onto S4 and KL0, and that's the second substitution. So fxy is a common generalization of these two terms here in the example, but it could in fact be literals. That's why we regrouped here the cases for terms and literals, because they are in fact very similar. Now having such common generalization is really fine, but as I said before, anti-unification is about finding the most specific generalization, because just any generalization is not really relevant. Here in the example, well, this can be seen as the best common generalization of both, but I could also simply have put a variable there, and that would have been a correct common generalization of the two terms. However, it wouldn't arguably be as specific, as interesting. So to stay parametric on that regard, we defined a quality function as being simply a function that associates a real value to any program object. And by program object, we mean terms, atoms, literals, goals, clauses, and predicates. So a quality function allows to say, okay, this is what we will consider a better generalization. To go back to our example before here, if I had the functor 1 that was here in the first term, but also in the second, then the generalization having f of 1 and then y would be a better generalization, because it's more specific. But to capture that, some might also consider, for example, that this generalization is maximal, because it's composed of as many terms, it represents as much common structure as possible. But this exact definition of what it means to have common structure is in fact very variable on the context. So this is our parameter omega here, which is a quality function. And for such a given quality function, we say simply that a common generalization is omega maximal is an omega mg if and only if it is maximal omega y. So if there doesn't exist another common generalization that has a higher quality. But remember that the quality could be, in fact, anything, depending on the application, as long as it's a real value function. So here we have an example of a useful quality function that we'll consider in the remainder of the presentation. So this quality function is based on the notion of norm. And a norm in terms is something that, for a given term, gives the size of the term. In this case, we define the size of a term as being the cardinality of the multiset of terms that appear in it. So if a term has a lot of imbricated functors, then it has a higher norm. And based on this norm, we can define the quality function, which we'll call tau here, which is one instance of the omega function that we discussed before. And this quality function tau, for a term, associates its norm. For a non-empty literal, it's considered 1, and that 1 will be useful later on, plus simply the sum of the quality of the imbricated terms in the arguments of the literal. And to a goal, a clause, or a predicate, simply the sum of the qualities of their constitutive parts. So that's a straightforward notion of quality function that we'll use here in our abstraction later on. So given that quality function now, how can we compute tau mg's, which are, remember, maximal generalization relative to tau for terms and literals? Well, first, we'll consider that we have some function phi that computes, that outputs a new variable name for any two terms that it has as arguments. This is simply a helper function that will help us define the rest of the things. Now we can define this anti-unification function that for two terms or literals, remember these could be literals, it outputs either the empty atom true if both literals are if these are literals but not based on the same on the same predicate name, sorry. So in that case, we simply say, well, it's true. It's the empty literal, which has quality of 0. If, however, the two symbols are the same and have the same arity, then we can recursively call the anti-unification function in each of the arguments. And whenever we have two different terms, then that's the third case there. If we have two different terms that we need to anti-unify, but these terms don't have the same arity, the functors don't have the same arity, or the terms are based on another functor or different functors, then we introduce a new variable that's specific for these two terms. And it's easy to see that this anti-unification, computing the tau maximal generalization of two terms or literals, can be computed in linear time.
But that will be the most specific one.
That will be the most specific.
Because the same term could appear several places in the subterms, and you want to take account of that.
If the same terms appears multiple times, then it will be handled by the recursive cases there, because if you have twice the same terms that are anti-unified with one another, it will be the same variable that will represent them. So this is considered to be, well, most specific in that regard. But
It's handled by the phi.
yeah, it's handled by the phi. And this is actually an interesting question, because indeed the tau function defines what we will call most specific generalizations. And in this work, we call them tau maximal generalizations, because we consider a quality function, whereas in the literature, often one quality function is given and is considered to, in fact, we don't even speak about quality functions, we simply say that's most specific. Here, we keep it parametric, and but to actually give an example of a concrete anti-unification operator, well, we need to instantiate omega, and here we use tau. So now we can define the anti-unification of other structures than atoms and literals, for example, goals, and this is straightforward. We say that a goal G is a generalization of G prime when there exists a substitution such that applied on G, well, we get a subset of G prime, because remember, goals are sets. And then we can again construct the notion of common generalization. A common generalization is simply for two goals, a goal that's more general than both these goals. That's a generalization of both these goals. Now let's go further and try to generalize clauses. When we have two clauses, we say that the first clause here, C, is more general, or is a generalization of the second clause there, C prime, when it has less arguments or the same number of arguments. There exists a substitution sigma, so this is usual, such that the goal is a generalization of the goal of C prime. So this is not new. What's new here is that we also need an injective argument mapping, which is a function that maps the arguments of the first clause, appearing in the head of the first clause, to the arguments of the other. The idea behind that is that when you have two predicates, maybe there are corresponding arguments. So in our example, for example, of course, next sum and take, we could see some correspondence of the arguments, but maybe we need to swap some arguments to see that correspondence. So we need to consider the order to not be fixed. So that's the idea behind that argument mapping. And of course, such that each of these terms, which are in the head of C, is itself a generalization of the corresponding term in the head of C prime. So this is what it means for a clause to be more general than another. So here, as you can see, we don't consider tau anymore. We're really speaking in a general sense. So as a simple example, the first clause here can be seen as a generalization of the second one, because although they have different names, this is not important here. It doesn't play a role in the definition. We can see that we can see a mapping from the first argument of P and the second argument of Q, and also going from the second argument of P on the first argument of Q, such that in fact we have a correspondence, and then still considering the same mappings, the same substitution, we can map also the literal here appearing in the body. So we are in the definition. C, the first clause is more general than the other. Now let's get one step even higher and go to predicates. If I have two predicates, in fact, I would need the clauses to be more general than the clauses of P to be more general than those of Q. Yes, but again, remember that the clauses are not ordered. So they are themselves in a set. So we say that P is more general than Q if it has less arguments. It has also less clauses, fewer clauses. There exists still an argument mapping remembering the relations between the arguments of P and the arguments of Q. But now we also need a close mapping between the clauses of P and mapping those on the clauses of Q, such that simply for each of the clauses in the domain of this gamma mapping, the clause in P is more general than the corresponding clause in Q. But always with the same involved argument mapping alpha, because the arguments could be in a different order in the predicates, but for all the clauses, it's the same order that needs to be considered. We can permute them, but always for all the clauses the same. And quite naturally, we can now define a common generalization of two predicates with respect to an argument mapping alpha and clause mapping gamma as a simpler predicate where each of the clause appearing in the predicate is more general than both the input clauses, with maybe different argument mappings, but such that these two argument mappings are coherent with one another. I won't go into the details here, but this simply says that the two argument mappings, in fact, are well defined so that the common generalization is a common generalization for both. Now let's go to our main contribution, which is an algorithm to anti-unify predicates. So let's get back to our example with take and next sum. And the idea is that we will have to build these alpha and gamma that allow to show that, to compute a common generalization. How can we do that? Well, what we introduced in the paper is an algorithm that does these computations in a greedy way. So first, we build a matrix containing the quality of, containing in each cell the quality of anti-unifying each pair of arguments. So we have a matrix corresponding to all the arguments, and we see for each pair of them how much quality it yields tau-wise to anti-unify them. And then we have a similar matrix for literals, because we also need to map the literals on one another. And then we greedily select the cells to obtain a high overall quality, while still allowing for some backtracking on the maximal cells. If we have, for example, two cells that are maximal quality-wise with a value of 10, for example, we'll put those two cells on a stack and explore the two possibilities. So the matrix is like this for the example, and this is the matrix on the level of the arguments. So as you can see, in fact, it could be more clear this way, because as you can see, we have the arguments on the left. These are the arguments of take, but of all the clauses. And on the top there, we have the arguments of next sum of all the clauses too. And then for each couple of those, in each cell, we put the quality, tau-wise, of anti-unifying this pair of arguments together. But in fact, consider, for example, that we select the underlined element there. What's interesting here is that when we select this element, we won't be able, we actually constrain the second argument of take to be mapped on the first argument of next sum. And we also constrain the third clause of take to be mapped on the third clause of next sum. So this is important because it will eliminate, in fact, a whole range of cells in the matrix. It will eliminate the cells involving only one of the selected clauses and those involving only one of the selected argument positions. So we can do the same for the literals, and the only relevant literals here are in the third clauses to have this matrix. And the idea of the algorithm is to greedily select the best possible cells. So in this example, we'll take the cell with value 3 here. And this will actually constrain some clauses to be mapped together. So since we mapped the third clauses together, we know that we consider this green rectangle here. And so we eliminate these two rectangles and these two. And we also eliminate all the cells where the second argument of take is mapped onto another than the first argument of next sum. And by greedily selecting those maximal cells at each iteration, we in fact can build a pretty good approximation of the generalization of the n-unification. And why do we need an approximation here? Well, it's because trying to get all the possible possibilities, all the argument mappings and the close mappings that could yield the best generalization in an exhaustive way, well, that would be, of course, problematic on a complexity level. So here, we really try to approximate this. And in the second matrix, we also have that when we select a cell, we also eliminate a whole range of other cells. I won't go into the details of the algorithm, and simply observe that the matrices are typically sparse. As we have seen in the example, there are a lot of zeros, in fact, in the matrices. So this allows the algorithm to run fairly quickly, and that we compute both mappings simultaneously. But we could imagine a version of the algorithm that favors, for example, the close mapping, that first computes the close mapping, and then only can compute the argument mapping. And the result, for example, is this generalization there, where each time you have a phi, it simply says that it's a new variable. And as we can see, it's a pretty good generalization because it says that there's one clause where we have simply a base case where we have a 0 appearing. Then we have a clause where we have the empty lists. And these two are clauses with no bodies. And then we have the recursive case here, when we have the different literals that are n-unified using the algorithm. So this is the first incarnation of the concept of predicates, most specific generalization, with the use here of a quality function tau. We would like to explore other quality functions. We would also like to explore the handling of recursive calls, which are here simply abstracted by a lambda term, but we still need to better handle the recursive calls because right now we simply consider them to be of quality 1 with one another. We would also like to minimize the number of different generalization variables to achieve even more specificity in the generalization, and then deriving a measure of distance among predicates based on the n-unification. Thank you.
Thank you. So we have time for questions. Are there any questions?
A very quick question about applying this. Can you give us some idea of the size of the search space? I mean, if you're given two procedures and you want to find suitable mappings to see whether there is a generalization or a useful generalization of them, I mean, is it a huge search space to do that, or are there some good heuristics that will guide you to finding the right mappings?
Without the heuristic, you mean? So the whole search space?
Yeah, the whole search space, and then with the heuristics.
The whole search space is, in fact, it's proportional to, you know, all the possible argument mappings. But this could be, it's a mapping from the arguments of one predicate to the other, but it can be incomplete mappings. So it's combinatory on that level because you could consider, you should consider all the possible.
The ejected mappings of the arguments.
Yeah. And then for each of these, you could consider all the possible close mappings, which which can be seen independently. So that actually explodes. I think it's I don't want to say to say a mistake here, but I think it's exponential. But with the heuristic, in the worst case, it's still exponential because in the worst case, we have a matrix where all the qualities are at 1. But we have observed that that typically when the predicates use different functors, use pattern matching, use recursivity, well then there are lots of zeros that appear and the search space is heavily reduced and it becomes, in the example here for example, it's polynomial, it's really simply resolves. Yeah.
Other questions?
Thank you very much. A very quick question. Have you tried another measures or not? And do you have any idea of which kind of measures could be good to do that?
That's actually a good question. Here we have considered the tau value, which is the term size. We have really favored the term size of the results. But in one of our other works, we had, for example, favored the number of different literals that are generalized. So it's like we put a 1 everywhere rather than having different values. So this is an example that we have already tried. But as I said, we'd like to try other quality functions. And in fact, it's related to the third point here. We would like to define a quality function that actually allows to give a higher quality to those generalizations that have less different variables. And this is not captured at all for now, but that has, for example, if you have a generalization that uses x, this means that there's a data flow link at each occurrence of the x. And with the phi function here, we achieve partly this, but we would like to investigate it further.
Okay.
Thank you.
Thank you very much.
Okay. So, if you have more questions to Gonzague, you can ask them later. Okay, so it's time to go to the next.
Thank you.
Thank the speaker, of course. Okay, so the next paper is a novel EGs-based framework for systematic propositional formula simplification by Jordina Frances de Mas and Juliana Bowles. Okay, and the presenter is Jordina.
Hello. So I'm going to tell you about a new framework to simplify propositional formula. And some of you might ask yourself, like, why propositional logic and why simplification? I mean, isn't that an old problem? Like, we all study higher order logic, fuzzy logic, unification, like all these very difficult problems. So it seems like if this should be solved already, and nowadays we have, we all know about SAT solvers that are able to solve huge problems with millions of clauses and hundreds of thousands of variables very quickly. But it turns out that these are not my words, are people working with solvers that said this. So many solvers are in fact a soup of heuristics. The most powerful nowadays, which are learning solvers, are very powerful but opaque, like a black box. No one really knows how to predict the performance because no one knows really what the solver is doing. More recently, we also have had machine learning solvers that produced amazing results, but apparently they don't scale very well. So all of this kind of points that there's more need for reasoning, more reasoning and less search. Another motivation for this talk is automated, quote-unquote, theorem provers, because if you have worked with theorem provers, they're usually less automated than one would expect. And some even nowadays use as a backend SAT solver, so actually they use Surge and the DPLL algorithm. Then, of course, we have the traditional ways of proving propositional formula or simplifying them, like natural deduction or sequent calculus, but they are not systematic enough in many cases. The search space is huge. And of course, things like truth tables, kernel maps, and so on explode very quickly, and they can just handle like not even 100 variables. So we need something more powerful for bigger problems. Then another problem is that most of these techniques, if not all, and especially solvers, they all require that we flatten the formula first. So you cannot just give any formula. It has to be transformed into a normal form, which usually in SAT solving is conjunction normal form. And this not only makes the problems way bigger, but it also adds a lot of redundancy and a lot of redundant variables. And in many cases, it's not even an equivalent problem. It's just equisatisfiable. So to summarize, there's basically a lot of search and a lot of redundancy that could be reduced, could be simplified, substituted by more reasoning. So our solution is generic, is systematic. It guarantees equivalence of problems, and it guarantees that the problem is monotonically reduced. So it never increases, because some of these approaches increase the size of the problem. And it also can handle nested formula, so a propositional formula in any shape. So as an example, this is an example of mini-zinc, how it would transform this very, I don't know if you can see my pointer. No, anyway. Like the constraint is like a super simple constraint, and then when it's flattened, it gets just that tiny thing gets this big, and it adds 3 redundant variables, and it puts it like that, and there's still search, when actually that's a super simple tautology that you can prove mathematically like in seconds, and it should be, the result should be that all the solutions are true. Or the absorption law even, I was surprised that it's not simplified automatically either. There's still search going on. So one wonders that if this time, you can imagine a bigger problem where it's formed by many small little parts like this that are very easy, but put together actually create huge problems that mathematically are very simple. So my approach is based on Peirce existential graphs, which is a non-symbolic and non-linear system, diagrammatic way of representing propositional formula, which is in fact equivalent to propositional logic. And it has just 3 elements. So one is the sheet of assertion, so the blank space, which means truth. And then you put the elements in it like you would in a linear fashion. And then you have the cats, these circles, the ovals, which mean negation. And everything in this space is an implicit conjunction. So basically, the first one, you have P and not Q. Because it's not ordered, that is obviously the same as not Q and P. In this case, you have not. Everything inside is negated, P and not Q. But this is actually an important shape, because obviously this also, we all know, that translates to not P or Q, which is P implies Q. So you can actually see this shape of 2 circles as an implication. And then obviously you can represent more and more things, but because it's not ordered, it gives a kind of canonical representation that in linear logic you could represent in many ways, and with many negations or implication or not, or if you transform it to C and F, it will look completely different, etc. So Peirce presented this elegant and easy to learn way of working with logic together with a sound and complete deductive system, which is equivalent to the sequent calculus that we all know. I don't have time to go into it, but this is it. Like, it's just these 6 rules, and for example, the double cat insertion or elimination is the same as double negation insertion or elimination. And the rules are very simple and very easy to understand. And just as an example, so for example, this theorem called the splendid theorem, which in symbolic logic takes 43 steps to prove. In Peirce's diagrammatic representation, it's just 7 steps. So you start from the blank space, and then because of the double negation introduction, you can do that, and then etc. The problem is that this has the same problem a bit than sequent, even if it's better in many ways than the classical approaches. It's still, going from the blank space. How do you know that you have to introduce first that, and then that, you know, it's not obvious, like there's many, from any step you could try many different ways to progress the proof, and like any mathematical proof is not clear. You know, the search space in your head or computationally is huge. So we take another approach. And then the second thing that we built, that we use for our approach is binary implication graphs, which are also widely known, especially in SAT, which is very obvious. If you have not X or Y, means that X implies Y, and it also means that not Y implies X, so you have this like the graph way of representing binary clauses. So then from these two graphs, we derived this rule, which is a bit ugly to show here, but basically it's easier to see with an example, which is if you have a formula and you have that A implies E, so not E implies A, right? So you can see that the colors connect with each other. So basically if you have, for example, E, F, G inside, you can see that you can match it with the other clause, and the second condition of the rule applies, which means that you can delete the not G inside the clause, and with the second one, you can match the three of them directly, so the first condition applies, so you can delete it automatically. So this in the classical approach, you would have to first take this formula and flatten it, and then try to apply subsumption or self-subsuming resolution to the whole thing. And if one doesn't work, then maybe you apply something else. But, well, this one is systematic in the sense that, as we will see, you always go from the outside to the inside. So in practice, I mean, we have implemented this, and in practice, so this is an example of binary implication graph of a very small problem. So we combine this rule with a widely known rule, which is equivalent literal substitution. So when you have, in the binary implication graph, when you have a strongly connected component, that tells you that those literals are equivalent. So in practice, we maintain a dictionary of equivalences of that, and we condense the binary implication graph, and we have also implemented lazy versions of transitive reduction and finding these strongly connected components. Because otherwise, I mean, if you implement any of these, like in the previous talk, naively, everything becomes quadratic automatically and very slow. We also represent, I mean, we derived our rules from the existential graphs and the binary implication graphs, but we represent it in practice as a directed acyclic hypergraph, which is this representation here. Which allows to find things very quickly, and you don't have to traverse the whole formula every time. We give priority to the smallest clauses because they are the ones that have the most power to reduce the other clauses, and then we also combine it with the very easy double cut elimination and this literal substitution that I just mentioned. So the properties of this rule is that, I mean, because it's reversible, it's equivalence preserving. So while many of the rules used in SAT only preserve equisatisfiability, this one guarantees that you have exactly the same problem with the same solutions. Since it is non-increasing in variables, clauses, and literals, we also know that terminates. You can apply it to any formula. You don't need to transform it before that to a flat version. And in this case, it generalizes all these very widely known techniques in propositional logic and in SAT solving, which many of them are used in SAT solving. So in just one pass, you apply all of this, instead of having to combine them in tricky ways or have to first apply one, then another one. You can do everything at once, which simplifies the process a lot. And it can also emulate even more difficult simplification or preprocessing rules, techniques that when restricted to the binary implication graph, which are computationally very expensive, but if we restrict them to this version, can be run until completion. But most importantly, there's no wasted search effort at all in this technique, and it's only reasoning. So we never have to backtrack. There's never a decision literal in the process. So then after this rule, this is the most basic rule, like the first rule that we came up with. But after that, we have introduced many other rules which would generalize this one and can achieve even more powerful reductions and generalize all the pre-processing techniques that we have known until now. And one of them, this is just an example of a factor how you can get from several clauses. Actually, you can extract a new unit clause, which then you can propagate very easily, or how we can find equalities between not just literals with literals, but literals with other clauses, and how we substitute that. But this is not in the paper, so I won't go into it. And then, with the implementation, we have also tested it as a proof of concept with a lot of set benchmarks, just to prove they can run in all these huge problems with millions of clauses and hundreds of thousands of variables. And we have achieved, SAT problems are known to, industrial problems, to have a lot of redundancy in them. So we achieve pretty big reductions, which is not surprising. And then we have compared it with the equivalence preserving pre-processing that they have in Minisat, and we have achieved some more reduction. But not only that, but if we apply the Minisat equisatisfiable rules after applying our rules, you can achieve even more reductions, up to an 11% more reductions. It is slower than the rules that are out there, but I think that's also not surprising because it's just me implementing this thing on my own, while solvers have been refined by big teams during decades, so it doesn't surprise me either that it's a bit slower. But in any case, it's more robust than, and we have to remember also that it's not the preprocessing inside solving. It simplifies the problem, but it's, again, equisatisfiability is very different from reducing a problem, maintaining equivalence, so all the solutions, and having this, you don't lose any. So basically, it's you conserve all the solutions, so it's good also for model counting, and so I think it's also understandable that it takes more time because you're actually solving the problem, not just saying if it's satisfiable or not. So in programming, the holy grail is that you state the problem and the computer solves it, but in propositional logic, some say that it's finding a mechanical way to systematize reasoning, or others see it as you give a proposition and then the holy grail is that the computer will tell you an interesting theorem, not just prove what you have to come up in your mind. Again, we already have systematic ways of doing this, like truth tables or the algebra of Boole, but of course, they explode very quickly. And as an example of what I was saying about theorem prover, so this is the vampire theorem prover proof of Peirce's law, which is this very simple law that I had put in Minising at the bottom. And then you can see how it goes. So it first negates the conjecture, so it will prove by contradiction, then it applies a rule, then it transforms it to ENNF form, it transforms it to CNF form, applies another rule that supposedly has found among many different rules, then it transforms it again to CNF. So there's a lot of transformation and manipulation to be able to apply these rules. Well, in our system, so this is the representation of that rule as an existential graph. And as we said, we start from the outermost smallest clause, so we would propagate the P in the outermost circle. And then following the rules, like you can delete the inner P, then you can delete the double cat, and then you have P or no P. So this is, the blank base is a tautology. So in just 3 steps, you can prove that. If you have also like simple problems that you can get in logic lessons at university, again, like if you have the natural deduction or secant calculus rules, like you have to decide like what way do you go, which inference rule do you apply first, which clever choice of identities do you choose? And if we represent it as an existential graph, that's the thing on the left as an existential graph, immediately, like we would first, like in the parsing already, we would delete the double cut because it's an obvious transformation, and then we would have C and not B. And then if we propagate one of the two very quickly in just one other step and another double negation elimination, we already reach the point that we have B or not B, so the whole thing disappears. So we don't even have to develop or go into the rest of the potentially very huge problem. And not only that, even better, like because the conclusion was given by someone, or you had to come up with the conclusion. But the beauty of this process is that if you just take the premises, so we wouldn't have the last bit of the existential graph, which is the conclusion. And if you work on that with very, very few steps, you reach the conclusion that A equals B equals C equals true. So actually, which from where you can deduce many other conclusions, not just that C implies B. And then compared to, for example, the DPLL algorithm, the Wikipedia example, and you can see all this testing and backtracking, like all this, oh, let's try if B is 1 or if B is 0. And with the same, with even less number of steps if you apply our rules. So here, you don't have any clauses smaller than 3, so we would start from the first one where you have the A, not B, and not C. And then a very naive approach would be to just go one by one, right? So you check the first clause with the second, you don't find anything with the third, and so on. But with our representation that I talked about before, which is the hypergraph, I mean, our inner representation in the implementation, you don't even have to go clause by clause. Directly, you would find that you have another clause that has A, B, and C. And then you can match them. And this tells you that you can delete that C. So now you have a clause of size 2, so you give priority to the smaller clause. So then you find where do you have A and B, and then you find that you have it here, and you can delete that B, and then you have again another binary clause which you can propagate, etc. So very quickly and very easily, you can deduce already that C has to be true, and then you can propagate this unit clause and delete these bits, and then you can do this. I mean, obviously, in the computer, you don't need all of these steps, but it's to visualize how simple it is, and that there's never a test or a backtrack. It's all equivalent transformations. And then actually you get to the point that this problem is equivalent to A equals B equals C equals D equals true. So you have not only simplified the problem, you have in fact solved the problem. So you know that this is not a solution, this is the only solution of this problem, which is way stronger than just deciding if a problem is satisfiable or not. So our approach is also very important in the field of sharp-side, which is model counting, or at least to give lower or upper bounds for the number of solutions. So as a conclusion, which I went very fast, so you see. Well, I can give more details, or we can have longer questions. So yeah, as a conclusion, our approach reduces the amount of search or wasted search and allows for more reasoning in propositional logic, automated reasoning. Every step that our approach, so every step in our approach is in fact a proof step, so you don't need also to develop proof, like to reconstruct the proof from what you're doing. It also helps understand the problems and the structure of the problems, which can help to develop better solving strategies or better solvers, better ways to sequence methods, and yeah, minimize search in general. You can think of it like Gaussian elimination that we all know, which is simple, it's systematic, it simplifies the problem. Of course, it has in this case, like we did the whole complexity study of this rule and the extensions of it, and like DPLA, like the worst time, the worst case time complexity is polynomial, but most of the techniques used nowadays in SAT with huge problems have those kind of worst case bounds, but like in the previous talk, in practice, the problems are quite sparse compared to what they could be, so their strategies, basically you never reach those kind of upper bounds in practice. And also because we never add, because in SAT some of the simplification techniques delete some clauses, but some add redundant clauses or redundant variables. So they actually in practice they have to use heuristics to stop that at some point because it could not terminate. Well, in our case, it's guaranteed to always reduce the problem, so it is guaranteed to terminate. And yeah, as someone said, I don't remember who, but that having a bound is good, but having a ways to characterize all the solutions of a problem reaching that bound is even better. So we think, as a conclusion, that this is a step forward on the quest for automation. And as future work, we could refine our implementation or find someone to refine it. We could also do way more experimentation than what we've done so far. We have already developed a lot of extensions to this simple rule, which are way more powerful and interesting, but we haven't implemented those yet. It would also be very interesting to extend this rule to first order logic, because actually existential graphs have a very, very easy extension to first order logic. So actually all these rules apply obviously to first order logic, but equivalence becomes even easier in that setting. So that'd be an interesting way of research. I'm pretty sure, I mean, this is not, like unipropagation is not refutation complete, but it would also be interesting to study if some of our rules or combination of rules are, or what conditions do we need so that our procedure is refutation complete. It would also be interesting to investigate the link. Actually, existential graphs are very easy to translate to any other propositional formula representation. And there are strong links to A and F or to and inverter graphs, so it would also be interesting to connect those. And it can also help with explainable AI. So that's it.
Thank you, Jordina.
Thank you.
Okay, so any questions?
Looks amazing, looks very promising, but I mean, have you done any experiments yet of using it as a preprocessor for existing SAT solvers?
Yeah.
And does it have, or do the SAT solvers just undo a lot of the
So where do I have it?
I mean, obviously, in some cases, it gives you something that's trivially satisfiable or non-satisfiable, but...
I think I had a slide, here. Sorry. I have it now back. Yeah, so I did do experiments with SAT problems and compared it to the preprocessor of Minisat.
Right, but what I'm asking is not what effect it had on the SAT competition benchmarks, but if you simplify it and then give it to, say the SAT solver that won the SAT competition, does it perform better than it did?
Yeah, it does. Yeah, so after this, here I just show the degree of reduction, but also I mean, actually it's very interesting because all the reductions perform faster, but then if we give it to, so if we reduce our output is faster, but if we give the same output to Miniset, which actually just changes the name of the variables, but it's exactly the same problem, just with relabeling. Then suddenly, exactly the same problem can be slower. Not that the previous ones, but basically it also shows how, like, what big impact the heuristics have. So just having variables renamed, the same problem can be solved in few steps, while the other one takes longer. Or even, because usually in separate processing they use a bounded variable elimination, so they delete a lot of variables in an equisatisfiable way. And that, of course, reduces the problem very fast, but then sometimes you get problems that were solvable and become unsolvable. So that's also what you get with some of their transformations. But all the reductions have, compared to the original one, go faster. Okay. Just because the degree of reduction is so big. But I'm sure there are problems that's not the case, but it's not our problem. It's not that the reduction is, it's just because how precisely my critique to SAT solving that it's.
But there might be pathological examples where your transformation actually makes some solver do worse on the same problem. I mean, you're saying that so far you found it always improves, but you're not sure whether it's always the case.
Yeah, I could think of many cases that would be the case, or even like we have in the extension rules. There's some that we allow some specific clauses to be added because actually they allow to traverse the graph or the problem faster. So if you have solvers that can use those clauses, actually that's what learning solvers do. Like they get a stronger clause and then they can solve it faster. So sometimes redundancy helps. But in our case, because we never do any transformation that is just reducing in an equisatisfiable way, actually I think any slowdown that we get is actually because of how the solvers have been implemented and tweaked to be able to be faster at something, but it's not really based on the logics or mathematics. It's just that they have been optimized in a way, like or heuristics that works better in something, but it should not, or because then that allows it cannot be generalized to other problems. Or.
So thank you again, Jordina. I think we can continue the discussion offline. The next presentation, which will be the last of this session, it is from static to dynamic access control policies via attribute-based category mining by Anna Bamberger and Maribel Fernandez. The presenter is Anna. Okay.
All right, I will briefly introduce our concept for a miner to mine access control policies based on what we call categories. So just a quick overview of the domain. The access control system is a selective restriction of access to resources based on principal attributes, resource or environmental attributes, and other factors such as timings or locations. And the motivations for this work are that there there's a variety of different access control models already available, which each have specific languages, properties, and techniques. You might be familiar with what is probably the most famous one, the role-based access control model, which is used by many organizations, whereby a role is assigned, or rather a static table of roles exists, and those are assigned by an administrator to users. And there are variations of this based on what we will use here, attributes. And there's finally the access control meta model, which is what we are working on, which is based on the primitive notion of a category, which I'll explain in a minute, which is essentially a logical formula. So the challenges that are faced in access control are, of course, growing data and complexity, so a larger potential for conflict and security leaks. There is a large administrative burden for static systems, whereby the administrator constantly has to consider any changes to the organization and any policies before being able to administer anything. And there are plenty of models available, but they are problematic for a number of different reasons. The RBAC model, static obviously, does not allow for dynamic switching between policies, but relies purely on the administrator and organizational documentation, which can obviously get very complex and difficult to manage. The ABAC model does not provide explainability because what it provides is a set of rules with no real connection between each other. And then again, it's up to the administrator to find combinations and meanings between those rules and to produce actually meaningful policies. So this is where we are proposing in an ideal state, automated category-based access control policy miner. This is a meta model. It's a unified meta model for all other models, which relies on wider definitions of categories. And those categories may include definitions based on roles, attributes, outputs of a computer program, and other things, but there's no limitation to any of these characteristics, so there's less potential for conflict. What's attractive about this model is that it is capable of dynamically switching categories once there is an event that occurred which requires a change and the model has picked up that event. So there's less manual intervention. And obviously because of this, because it is grounded in logical formulas and axioms, it provides a better understanding and explainability of how it mines its policies, which, of course, it's very important in the area of security. So our key contributions for this piece of work, we present a new approach to mine the category-based policies defined by what, in this case, attributes. Again, reminder, they can be defined by something else, but here we're choosing attributes. And we seek our data from access control matrices and RBAC policies. That is not restrictive again. We can use logs and we can use organizational policies and other things. So the policies that are synthesized by the miner are category definitions. So those are formulas involving attributes and the corresponding values, and the list of any action that is permitted for each such category. And combined with our CBAC axioms, those define what are valid authorizations. And this miner wants to be capable of producing both dynamic as well as static, if so required, policies, and also explainable features for policy generation. So the category-based meta model is a core set of principles of access control and can be specialized for any number of applications. Because it is a meta model, it abstracts away any complexities. It is a generalization which can be used to filter out specifics for a role-based model, an attribute-based model, which is what we're doing here, and anything in between. It is formally defined, so it is an axiomatic approach to compare policies and understand what the consequences of changes are, and therefore also prove the properties of policies and how those policies combine. The entities are categories. Those categories are defined by principals, so users of the system, who receive authorizations via actions to act on resources. Resources can be databases, anything that requires access. And as well as what we refer to as situational identifiers, locations, times, anything else. And a category is a class or group to which this combination of entities, principal, actions, and resources, as well as the identifiers, belong. And there are particular cases such as roles, attributes, and whatnot. So these are the relationships between entities. The first two are identical. It's just one applies to principals, the other one applies to resources. And we're saying that if a principal belongs to a certain principal category, then it is assigned to that category based on the attributes that that principal displays. Same for resources. Then there is a permission category assignment, which we call ARCA. So we say, if there is an action that's authorized on one entity category with another opposite entity category, then that forms one assignment. And finally, once we have that, we can derive individual authorizations, or PAR, whereby we say, if a principal from that category may perform that action on that resource in that resource group, then this is a legitimate authorization and can be issued. Category-based access control is a very basic category-based policy, so it's a tuple consisting of PCA, ARCA, and PAR with those entities that I just spoke about. And we say that because it is general, because it doesn't limit itself to any characteristics, any other models, such as ABAC or RBAC or the discretionary model or mandatory or anything else, can be derived from that. And so we can say that they are really subsets of that meta model. And this is an example to show what is meant, what's the difference between static and dynamic. So this would be a classic RBAC table, where you have principals, principal metadata values, same for resources, and the action. So what would happen is, if a user arrives, and the user requests some access, and there's no indication of where that user is supposed to belong, then the administrator needs to step in, needs to figure out what that user's access should be, and needs to assign them something in that table. This is where dynamicity would provide a benefit. So you see the two categories two groups rather on the left, one in orange, one in green. Orange is the original category, or group. That is what the user had based on the metadata values. But now that user has changed. This is just an example, can be anything else. So now the user's access should be something different because we see that the authorization, the action, which is assigned to that group, is in one instance assigned users, in the other instance, right, so more permissive. So in the previous slide, in this instance, if that happened, we would need to go through the administrator, who would need to go through the policy, the organizational policy, through everything that they are aware of, and figure out if this is legitimate. For the CBAC model, that is not necessary because authorizations are assigned to the existing categories. So if the user arrives and has those attributes, and the system knows that there is an action assigned to that, and that action is associated with a specific resource category, then the system automatically puts the user into that category. And this is what it would look like. So we have on the left all the users that belong to the same category with the same action on the same resources. So that is what the completed mining concept should look like. We start out with logs, can be something different. We do data pre-processing, which is the green box. Don't know if you can see that. Where we can separate grant from deny actions. And then we create the categories, which are the 3 blue boxes. That is the core miner. So the miner goes in, figures out what are the correct categories, then it checks, are those categories correct against the logs? And if they are, then those categories are issued. If not, they're not. The algorithm details. So it's a combination of an NLP-based, which is used to assess similarity of what entities should be put together into one category and what not. And a subsequent FP growth-based check to make sure that any members that have been assigned to the same category actually carry the same authorizations with regards to the same opposite resource. If that is the case, if that is not the case, they will be split. If it is found that there are members from different similarity groups, which should actually be, because they carry the same authorizations, they are merged. And that is one of the goals of the miner, to create a minimum set of categories because of this technique. And so the outputs are the newly defined category definitions. We have a proof of correctness. So the miner terminates, the outputs are final, and it produces a list of category definitions, as well as any inconsistencies that may arise. And also, because we're looking for a minimum number of categories, and because we say that the RBAC miner, which is an NP hard problem, if that is derived from the CBAC problem, then CBAC is also NP hard. We have continued challenges. So there are characteristics other than the ones that are defined by the model, which may be required. For example, title, length of employment, and we may not necessarily know what those are. We may not know what the relevance of characteristics might be. We don't know what to do with unknown users. And requirements may change. So the system must be capable of dynamically adjusting to that. And then the future for our work would be to assess what that feature relevance is and what context means, because even if an attribute is the same, given a different context, it might actually mean something different. And so the miner needs to be able to understand that. We aim to use category parameters to predict what future categories might be based on existing information, such as, for example, user risk factors, and also external information. We want to continue recognizing category equivalence, even where attributes might be different, which is what I explained. And finally, if we have one attribute which is associated with one action, does that apply to a similar attribute? So for example, should we merge somebody who can delete with somebody who can write, if that's all the information that we have? And any questions?
John. Okay.
You were saying that at the beginning, at this first step, where you were looking at the logs, figure out what's been done in the past, you could use other things than logs. is there any specific category of things that you could be using, or do you have examples what else might work there?
Yes, so logs are good examples because we can assume that they're the ground of truth. If there's a principle associated with an action and a resource, then we assume that that should be correct, and if it's not, then obviously policy has a problem. But other grounds of truth would be policies, existing policies of the company, and they don't need, or the organization, and they don't need to be category-based, because that's the whole point of the miner. It can handle such situations. But also things such as what I mentioned here. If we get information about the user's history, for example, the user's medical data in case of where, for example, a medical emergency access might be required, then given those risk factors, or given that history, can we predict that there's going to be a situation tomorrow, in a week's time, whatever, when emergency access will be required? So that is something that we have not been working with yet, but it would be an interesting future endeavor.
More questions? No? So I have one. So do you think that some forms of explicit negation of authorizations make sense in this context or not? I mean, someone or some rule or some category who's not authorized to do something.
You can, of course, have a list of anything that's prohibited, and it's possible to do that. But the problem with that is it creates an if list of all the conditions that you want to introduce, and we're trying to get away from that. We're trying to have the algorithm recognize what is required to get into that category. And if you don't have what is required, then you simply don't get in. So yes, you can have explicit negations, but I think that would add to the complexity of the algorithm, and we would like something, and it would also take away from its autonomy.
Okay, thank you. So.
So welcome back to the sixth and last session of Lobster. And in this very final session, we will have actually a speaker that is going to present the best paper, or the paper that got the best paper award. So that's Fabio Fioravanti. Sorry. Going to talk about constrained horn clauses satisfiability via catamorphic abstractions. Thank you.
Okay. Thank you. So this is joint work with Emanuele De Angelis, Alberto Pettorossi, and Maurizio Proietti. And I will start by giving a brief overview of the use, about the use of constraint horn clauses in program verification. Then we will focus on the use of constraint horn clauses that use algebraic data types, such as lists and trees. And here we are interested in properties that are specified by using catamorphisms that you can think about as total functions or functional predicates in this case, with a fixed recursion schemata. And then I will show you our transformation that is based on transformation rules and is guaranteed to terminate and preserve the satisfiability of the clauses, and is based on the adaptation of the usual rules for defining, unfolding, and some other rules that are specifically conceived for dealing with catamorphisms and algebraic data types. And then I will show you the experimental evaluation, the results of the experimental evaluation. So constraint clauses are actually the same as constraint logic programs and Prolog. They share the same syntax and semantics, but usually they're not intended for direct execution, but are instead used as an intermediate language for expressing the semantics of programming languages and properties. So usually one translates the program and the property to constraint clauses and then checks their satisfiability. If the property is valid, if and only if the clauses are satisfiable. This is the standard approach. And horn clauses can be used for verifying properties of different kinds, partial correctness, relational properties, termination, resource consumption, and so on. And we can derive clauses starting from programs that use different paradigms. Imperative, object-oriented, functional, smart contracts. There is a workshop. Maybe many of you know that there's a workshop that is organized every year since 2014, and it's called SCVS, or Close Verification Synthesis. That is a very interesting workshop, so take note of it in case you want to submit a paper, because I'm the promoter, one of the promoters of the workshop. I would like to attract you, to invite you to contribute. And there's a CSC competition of solvers, and there are very good solvers for checking satisfiability of CSCs, such as Z3, Eldarica, Golem, and many others. CSCs are used by several communities, other than Lobster, but also ICLP, CAV, previously in PLDI, in Popl, Takas, and so on. And they're also used in industry. Microsoft, Amazon use CSCs, and Ethereum uses CSCs. In particular, for those of you who know Ethereum, the blockchain platform for smart contracts written in the Solidity language, and the Solidity compiler as a model checker that translates the solidity code to Horn clauses and then checks the satisfiability and the correctness of the code using backend CHC solvers, just to have an overview about the use of clauses or program verification. Then, however, state-of-the-art solvers have difficulties improving satisfiability of clauses that contain algebraic data types such as lists and trees. So instead of extending the CHC satisfiability checking in order to deal with these lists and trees, these ADTs, we follow a transformational approach by which we transform the clauses into an equisatisfiable set of clauses. And the transformation, as I told you, preserves satisfiability. So the initial set of clauses is satisfiable if and only if the final set is. And the transformation always terminates when properties are specified via catamorphism. The experimental results show that the transformation improves the effectiveness of the CHC solvers that were not designed for dealing for ADTs. And in this paper, we improve over the work we did we presented in previous papers, as we do not need auxiliary lemmas for specifying properties of auxiliary functions used by the programs that we are going to verify. No information for multiple queries, but instead for each ADT sort, say in the example list of integers, we define the set of relevant catamorphisms. We call it the catamorphic abstraction. And then we also augment the clauses with ADTs using clauses without ADTs. And this is a crucial step that enables standard CHC solvers to be more effective in discovering the relation among variables that are useful for proving the satisfiability of the clauses. The satisfiability or the unsatisfiability, of course. What are catamorphisms? So intuitively, they are predicates that are total and functional with respect to some of their arguments, and are defined by simple recursion schemata. Examples as list length or tree size. Let's see in this slide a template for the list catamorphisms. We have two clauses here. One clause deals with the empty list, and the other clause deals with the non-empty list with just one argument exposed. And it calls the predicate name is h, and h also there's a call to h in the body on the tail of the list. This recursive call produces a result, and the result, the final result, is obtained by combining the result R with possibly with h. Okay, by combine 1, h, r, res. Where combine 1 and combine 2 below are total functional predicates or constraints, not necessarily catamorphisms themselves. So for instance, the predicate computing the length of a list matches the schema. As you see, length of the empty list is 0. The length of non-empty list is computed as by adding 1 to the length of the tail of the list. Okay? And the binary tree catamorphism schema instead is very similar, but instead it has a clause for the base case of the tree. There's a leaf node, a leaf, and then the recursive case exposes the node, the element, and the left and the right subtrees, and there's two recursive calls to the left and right subtrees. So the predicate computing the size of a binary tree you can see that is an instance of this schema. Actually, we extend this, the standard notion of catamorphism by allowing extra parameters that allows us to define predicates that says, for instance, for specifying that X is less or equal than all elements of a list L. For a list, or for counting the number of occurrences of an element in a tree or in a list. By further extension, we add extra function calls. In this way, we are also able to expect the properties such as the one saying that a list is sorted. And for trees, by adding extra function calls, we can specify even the binary search properties of a tree. So we can see that a tree is a binary search tree. So let's start with an example. Let us consider the program specifying the predicate double, where double xz holds if and only if z is the result of appending x to itself. So the definition of double is in this row. We create a copy of x, and we append x to this copy, thereby producing z. Then there's the usual definition for append. And we have a catamorphism here, count, that counts the number of occurrences of an element in a list, and the result is in the last argument. In the query, the property we want to verify is that there is no element that occurs in Z and not the number of times, because we are duplicating a list, so then no element can occur not the number of times. We can write it this way in the query form. So we put here the negation of the properties that M is odd, and this should be false. Okay? How do we proceed now? For every ADT sort, tau, we define a catamorphic abstraction that is a conjunction of catamorphism that we are interested in. So if tau is an ADT sort, we introduce a conjunction of katas, like you see here, where t is an ADT variable, and x and y's are tuples of distinct basic variable, not ADTs, just basic variable. By basic variable, we mean integer, booleans, and so on. Okay? And that are pairwise disjoint. These katas are distinct catamorphisms. So, for instance, for the list of integers, going back to the example, for the list of integers, we can introduce the catamorphic abstraction that says that we are interested in counting the number of occurrences of elements in a list. And so the kata is just this one, count x ln. Then, given the catamorphic abstractions for all the ADT sorts used by the program, then for each program predicate, we get a catamorphic abstraction specification of this form, where P is a program predicate, and this this is a conjunction of atoms where these are catamorphins, and X is a tuple of distinct basic variables. TIs, these variables underlined here, T1, Tk, are all the T variables occurring in Z, in the code, and they're possibly not distinct. And X and VIs are tuples, again, of distinct basic variables that do not occur in Z. So, for instance, going back to our example, for double, since X and Z are list of integers, and our catamorphic abstraction for list of integers tells us that we are interested in counting the occurrences of elements in a list, we get this conjunction. We count the occurrences of X in the first argument, and N1 is the number of such occurrences, and N2 is the number of occurrences of X, or element X, in the second ADT argument Z. This is the result of appending the two lists. And so on for the other program predicates. Then we proceed by transformation. We start with clauses that encode the program of interest, the query, and the catamorphic abstraction. And we start by defining new predicates that contain just one program predicate and some catamorphins for properties. Then we unfold the program predicates once, and then we unfold the catamorphins with non-variable ADT arguments as long as possible, as long due to the structure of the catamorphism, this is guaranteed to terminate. Then we possibly add catamorphism atoms to the body of unfolded clauses, and then we fold using the definition we introduced during the first step, and we replace in the body of clauses goals with heads of clauses added by definition. At the end, we derive a new set of clauses by erasing ADT arguments, and we add the atoms with the erased atoms to the folded clauses. Let's see each step briefly. Then definition are introduced for definition for new predicates. Predicates not occurring in the original program are automatically introduced using the query and the catamorphic abstractions for the program predicates. So we introduce in our example these three definitions. Then we unfold the program predicate in a definition once. So if we have this definition clause here, we unfold double, and we replace double with the conjunction equal append. Then we repeatedly unfold catamorphins with non-variable ADT arguments. In this case, there are no such catamorphins. And then we repeatedly apply catamorphins functionality. Again, there is no such, this is not applicable in this case, but this allows us, for instance, to replace this conjunction of two catamorphins, count AB C1, count AB C2, by this conjunction where we drop one of the catamorphism atoms and replace it by an equality, because we recall that these are functional. So C1 should be equal to C2. It's not. We don't need both. Then, using the catamorphic abstraction specification, we possibly add catamorphism atoms to the bodies of the unfolded clauses. So for instance, this is an unfolded clause, and the catamorphic abstract specification includes this expression that says that for EQ, I'm interested in counting the occurrences of X in the first list and in the second list. And going back here, I see there's just a count on the first list. There is no count on G. This is the second argument. And so I add the count for it. Note that I is a fresh variable, so I'm preserving satisfiability. I is existential, can be anything. Then, using the definitions, I fold, that is, I replace an instance of the body of the definition by the corresponding head. If we go back to this slide, we see that we had a clause with EQ and append. These are the definitions that have append and EQ in the body, and we replace EQ and append and the catamorphins that are bound to the variables occurring in these atoms, by the corresponding head, nu2 and nu3. Note that folding derives clauses when there are no catamorphins, there are no program predicates, just new predicates, the predicates we introduced by definition. Now we derive new clauses by erasing ADT arguments from the clauses that we have obtained by folding. So you can see the folded clause here with the ADT arguments underlined, and we derive a new version of this clause where for each predicate symbol we introduce a new predicate symbol without the ADTs. So new one, because new one without ADTs, we just project away these arguments. We drop them. And actually, this is, and we produce an abstraction of the previous set of clauses. Existing solvers are good on clauses without ADTs, but since this is an abstraction, this is good for proving satisfiability, but not for proving unsatisfiability, because if you prove unsatisfiability in the abstraction, it could be a spurious counterexample. And but we do not use this abstraction directly. Instead, we add this abstraction to the equisatisfiable clauses. By doing so, solvers are much more effective in discovering the relation between the constraint relating these basic variables. And so we derive this final set of clauses starting from the original clauses for double, the query, and the catamorphic abstraction. Now I'm ready to show you the results of the experimental evaluation that has been performed by using VERICAT apps. They use this very catamorphic abstraction that is implemented on top of VERIMAP. This is our original system for CSC transformation verification. So we, starting from our discloses, the query, and the catamorphic abstraction, we apply this transformation algorithm and produce clauses that contain ADTs, clauses without ADTs. Then we translate this clause to the SMTLib format, and then we invoke the state-of-the-art solvers, such as Z3 and Eldarica, and then the output is either SAT or unsat or timeout. That's unknown. And the benchmark consists of 150 programs for concatenating, permuting, reversing, and sorting over list of integers. For sorting, we use different algorithms: bubble sort, heap sort, insertion, merge, quick sort, selection, and tree sort. For element insertion, deletion in binary search trees. The properties that can be defined by using catamorphies include the length of the list, tree size, tree height, minimum and maximum element of a list or a tree, sortedness of a list, binary search tree property, heap property, balanced tree, sum of elements of a list of a tree, or content of a list as a set or multi-set of elements. In this table, I will show you the result of our experimental evaluation. In the first column, we have the program, list deletion, permutation, reversal, sorting algorithms, binary search tree. And we have properties, SAT and unsat properties. So properties should be either valid or not valid, so the output is SAT or unsat, respectively. And in these columns, we have the results of running Eldarica before source and after the transformation. So we run Eldarica on the source clauses before the transformation, and we also run Eldarica on the source clauses after transformation. And the same we do for Z3, before and after. And the last column shows the transformation time in seconds. The first observation is that state-of-the-art solvers are very good at proving unsatisfiability, not satisfiability. That is a finding bugs, not proving that there is no bug. So for instance, Eldarica on the source clauses clauses is able to prove 5 SAT properties and 69 unsat. But after the transformation, it's able to prove 39 SAT and 59 unsat. So there's an increase in the number of SAT and a decrease in the number of unsat. This is probably due to the fact that Eldarica is often very close to the timeout, even for the properties that are proved unsat. So maybe giving some more time to be able to prove them. Whereas if we look at the result for Z3, Z3 is extremely effective at proving unsatisfiability. It's able indeed to prove the unsatisfiability of all 75 properties, but of no satisfiability property. So 0, 75 before, and after transformation, the result is that it's able to prove the satisfiability of 70 and still be able to prove the unsatisfiability of all the 75 properties. So overall, we get a plus 70 satisfiable properties with the solving time below 1 second. The other observation is that the transformation introduces a small overhead because the transformation time is almost always below 1 second, very fast. So this is a complete and sound transformation that works well for verifying property of clauses with ADTs written using catamorphism. The advantage of using the transformation approach is that we are able to separate the inductive reasoning done by the transformation from the solving part done by the CHC solvers. And this is also largely independent from the constraint theory. It can be, so we usually linear integer arithmetic and booleans, but we can use could use any constraint theory supported by the SMT solvers. What about the ongoing future work? We are working on the automatic discovery of useful catamorphisms for further reducing the burden of the programmer and specifying the properties of interest and extend the applicability condition of the method. We are using catamorphisms because they have good property, they ensure us the termination, and they're functional, but we would like to relax also that and a bit still guaranteeing the termination of the process. We would like also to compare with other solvers that were specifically designed for working on ADTs, the most notable of which is Racer Z3, Popple 2022, but it's very good. It's very good on the unsat instances again, but even in that version, it was less precise than the tool we used 2 years ago. So we are confident that we are better. This is an issue that different input formats, so they're not just SMT-lib clauses. You have to annotate predicates and write extra stuff. So it's not very easy to do an extensive comparison. Maybe we'll do it in the next edition of the CHC comp. And a medium-term objective is using our transformation approach as a backend for program verifier, like Daphne, Stainless, and Y3, for instance. So that's all. Thank you.
Thank you very much for that. Any questions?
So thank you very much for the great talk. I was wondering about extensions of those catamorphisms with some kind of perhaps. First, can you have ADTs as results of those catamorphisms, or is it really important that, let's say, the result of the catamorphism is a base type, a base sort for the Horn constraints?
Actually, as the result, you mean as the output?
Yes, because if you can extend the results to other ADTs, you may be able to encode some effectful iteration on ADTs. So for example, if the output of some list iteration is a sum type, you can represent an exception that could occur during traversal of the list. And that might be applicable in quite a few settings, I believe, maybe.
Actually, currently we do not allow ADTs as outputs, but of course they can be extended. For instance, you could extend. You have to be very careful, however, on the structure. So if you have to be sure that by doing so, you don't lose the termination by allowing some ADT arguments to go. And so you're not able to unfold unrestrictedly, but you have to stop somewhere, somehow, and maybe generalize, introduce some generalization mechanism in order to deal with them.
Okay, thank you.
Thank you.
Thanks. Very interesting. And I was just wondering whether you saw any connection to the kind of things that Manuel was talking about this morning. I mean, is there some way that you can use catamorphisms to design an abstract domain which will then help you to verify some assertion? I mean, he used similar examples, sortedness and so on.
Yeah, indeed, one of the ideas was to use the Chow analyzer in order to verify whether predicate is actually a catamorphism, so to verify whether it's...
To verify whether a predicate is a catamorphism?
Is a catamorphism, yeah. Because in principle, you don't know whether it is. Now we assume that that some predicates are catamorphisms, because they are total and functional. But in principle, you should be able to discover it from your input by guessing which could be the output argument, and check whether it's functional and whether it's total and so on. So one possible direction is that of using the Chow analyzer for discovering this information. But of course, we are assuming that these predicates are catamorphism, but we could also verify by using our other techniques. But that's
maybe just a final question from me. You focus only on transformations that are equi-satisfiable. Where does this restriction come in, and why?
Because
maybe I
we
missed
also would like to check whether a property is invalid. That's not hold.
Okay.
So if you, in previous work, we produce an abstraction. So if you got an answer unsat on an abstraction, you're not sure whether it comes from the real traces, so to say, the real paths inside, or in the space you introduce by abstracting.
Okay.
And so that's why we are interested in preserving satisfiability.
Okay, so thank you very much. There was no further questions. Thank you very much. And so we move to the very final talk of Lobster, which is a short talk by John Gallagher on transforming big step to small step semantics using interpreter specialization. Thank you.
Good. So in a short time, I hope to show you what we're doing. It's very much work in progress, research in progress as a short paper. And my co-authors, Manuel, Jose, and Pedro, have had many discussions about the use of semantics, big step and small step semantics, for transforming programs into horn clauses, which has arisen in a couple of papers today. And so both big step and small step semantics can be relevant, and so the question arose actually from another paper we presented about transforming, say, imperative programs into horn clauses, about whether you could use similar techniques, interpreter specialization, to transform the actual semantics, big step semantics, into small step semantics. So big step semantics, I mean, obviously formal semantics is really fundamental to any kind of formal verification, reasoning about programs. Operational semantics dominates these days. I mean, there's axiomatic semantics as well, which has a very close relation to big step semantics. But both big step and small step semantics are useful for different purposes in in verification tasks. A lot of people in working on types prefer small step semantics for verifying type soundness, for example. Big step semantics is often used for resource analysis, among other things, and other verification tasks. It was developed by Gilles Kahn in the 1980s as a kind of proof theoretic approach to operational semantics, and it's based on structural decomposition of statements. So the classical example is the statement composition in an imperative language. I use the down arrow for the big step. In the paper, I used a long straight arrow, but I think it's clearer on the slides to have a down arrow for the big step and a straight arrow for the small step. So the big arrow, big step, if statement S1 in state sigma 0 evaluates in total, a complete evaluation, leaving state sigma 1, and similarly S2 evaluates in state sigma 1 to sigma 2, then the composition S1, S2 evaluates to in state 0 to state 2, state sigma 2. So it's very structural, compositional. It's not quite compositional because if you look at the while statement, obviously it will, the while statement will have appear, the while construct will appear above and below the line. But in some cases where there's no subformulas, like an assignment statement, for example, then you have an axiom which has just got something below the line and possibly a condition. In small step semantics developed by Plotkin, actually earlier than Kahn's work, very early 80s, an execution of a program also deals with configurations of a state, a statement, and an environment or a store of some kind. And a small step takes you from a statement in a given state to the next statement in the next state. And then a complete execution is a run of small steps, so say the transitive closure of the small step relation. And in fact, you typically have a special small step for the final step, which only leaves a state or a value. If you're dealing with something like the lambda calculus, then it deals with values rather than returning a final state. But that's a minor difference. So to look at statement composition again, we have S1 semicolon S2, and the first rule eats away at S1 in small steps until it's finished and then moves to S2. So if S1 in one small step goes to S1 prime, then S1 semicolon S2 goes to S1 prime semicolon S2 in the next state. And then if S1 does terminate in one small step, then we move with that resulting state to the next state. And actually, for axioms, for things with nothing above the line, then the small steps and the big steps are the same. They terminate in one small step. So here's an example. It's kind of essential to our work that we represent everything as Horn clauses. Well, perhaps not essential, but because you could formulate it in other ways, obviously, but it's very convenient and very direct. So if you look at a textbook example, here's the call by value lambda calculus, some big step rules. We can see that we can just encode them directly as Horn clauses. And in fact, judgments of all kinds are Horn clauses. If you providing that you can encode the statements and the state as first order terms, then the arrow is just a predicate. And we have the head below the line and the body above the line. So I mean, you can see that here we have 3 premises plus a construction for updating the state, and they are the body of the corresponding Horn clause rule. And then, of course, we have to encode in some suitable Horn clauses the subsidiary predicates, like finding something in the state and updating the state. So we have big step semantics. We can directly render those as Horn clauses. And then the idea of interpreter specialization, I'll just briefly go through. So it's a well-established idea, going back to Futamura in 1971, where he showed that specializing an interpreter with respect to a source program is analogous to compiling that program into the language of the interpreter. So if you happen to have an interpreter in the same language as the source program, then you can regard the first Futamura projection as transforming the source program into another source program, which encodes the semantics that are embodied by the interpreter. So that might be a non-standard semantics. So in the context of this paper, if we regard our big step rules B as an evaluator, we can say that if we evaluate a given statement and state with the function represented by the big step, we will get the final value. But then what we're going to do, what we did in this work, is to write an interpreter that that imposes some non-standard semantics on the big step rule, so it executes B in small steps. So the interpreter, when applied to the big step rules and an initial state, an initial configuration, will yield the same value, assuming that the interpreter is correct. And then the specialization is that we specialize the interpreter with respect to B, but with an unknown initial state, represented by this. PE is a specializer, a partial evaluator. And this turns out, if we do it right, will contain the small step semantic rules corresponding to B. So we've transformed B into another set of horn clauses derived from the interpreter that, as we'll see from an example, literally line for line contain the small step rules. Now then, then that's something that you could then apply directly to an initial configuration, and you would get the same result, V. So how do we write this interpreter? I'm just going to sketch it here because there's a lot of detail which is in the paper and I don't have time to go through it. But supposing we take statement composition again. So we have a rule, a big step rule, but we're going to start by evaluating the first premise for the execution of S1. And let's say, well, we're going to turn this into a run going in small steps from S1 sigma 0, small step, small step, small step, to a final state sigma 1. Well, the first premise either has a run which terminates immediately, or it has a first step, small step, followed by a big step for the rest of the run, right? So we split off the first small step. So this is how we reason, and I'll show you the clauses of the interpreter in a second. So the remaining computation then is either the second premise, which is the second premise of the big step rule, or it's a big step from S1 prime, sigma 1 prime, the result of executing one small step on the original S1, and then the second premise. Now, in the first case, the small step rule then that will derive from the partially evaluated interpreter will be, if we do a small step on S1 and it terminates right away, then from S1 semicolon S2, we'll just go straight to S2, as we'd expect. In the second case, we've got two goals, and the way we make it the next state is to fold those two goals. They are an instance of the same rule that we used to construct the premise in the first place. So we can fold it to get S1 prime semicolon S2, sigma prime 0, big step to sigma 2. So the rule becomes, if we do one small step, then we make one small step. This is the folding of the remaining premises. Right. In the paper, we explain how when you can fold. If you can't fold, you can't always fold. For example, you move from S1 sigma 0, but you may need either S1 or sigma later on in the second premise, for example. So you can't just throw them away and replace them by S1 prime, sigma 0 prime. And then we have a way of looking at the structure of the remaining premises and creating an auxiliary big step rule and inventing a new syntax constructor. All the other work on, in the paper we review some other work on transforming big step to small step, and they all do something similar. Of course, not surprisingly, there are many common features. We just do it by an interpreter rather than a directly defined transformation. But they all get auxiliary new syntax constructors. But have to look at the paper to do that. So here, having tried to motivate how we interpret the big step rules in a small step way. Here are the first few clauses of the interpreter that we specialize. So first of all, we define a run, because the small step and the big step are not exactly the same. To make them equivalent, we have to add the notion of a run, the transitive closure of the small steps, to make it equivalent to the big step. So we define a run, which is either a terminated. The empty list represents no steps remaining, no configuration remaining, or something that is terminated. Or if we have a single big step call A, then we execute a small step on it, getting A's 1, which is either terminated or another step, A1, and run that. And then the small step itself has three cases. The axiom, which just looks for a rule, and, well, there may be some conditions, but when you've evaluated, though, there's nothing else above the line, so that will terminate. I didn't discuss also, we also regard as a small step big step rules which essentially just translate one construct into another. I mean, it's common to define, let's say, a for statement into an equivalent while statement with an initialization. So we regard those as small steps as well. But I'll skip over that. So the interesting case is this one. If you've got a rule with at least two premises, and the first one is a big step, then you do a small step on the first premise, B1, and then there's an operation to try to fold that to get the remaining step encoded as a single big step, A's. And it could be, that could also terminate, so we can't say single bracket A1 or something. We have to say it's either empty or a single goal. So I'm going to give you a quick demo. I hope I've just about time. So if I look at, I mean, Kahn's original paper contained the big step semantics for mini-ML. So it's got let rec and let and application and a if then else statement. So it's a reasonably comprehensive lambda calculus. Then, as I showed, you can just translate that literally line for line, one-to-one into horn clauses. Here's the rule for let rec, for example. And then some subsidiary predicates for looking up the state and so on. So then what I've got is a script which applies the partial evaluator to the interpreter with respect to that set of big step rules. When we look at that, mini-ML, here we are. You can see that it was created today at 1453, so I didn't do it earlier. So the partially evaluated result contains the run predicate, and then this is the output of Logen, the partial evaluator I'm using, Michael Leuschel's Logen system. But the small step rules, there's quite a lot of them actually in this case, because you have to create quite a few subsidiary constructors. But they are in a form, always in the form of the head is what's below the line and the body is what's above the line. In all cases, it's either got a single small step above the line or something which is just got to be evaluated like one of these side conditions. So I mean, I have written a script which translates this directly into defrac expression, LaTeX expressions. It's literally a one-to-one. It's just a syntactic transformation. So we've done a number of examples from the literature, and yeah, there are small differences from what other people have produced. Let's go back to the slides. But there are minor differences. I mean, we are getting results, and furthermore, we can run all the interpreters. As I say, future work is to do some proofs of this, but we have some validation in the sense that we can run the original big step on some examples, we can do the transformation and run the small step, the transformed interpreter with the small step rules and see that we get the same things. So first of all, we can check the correctness of the interpreter, so we get the expected results. So we can do extensive testing, is what I'm saying, which is no substitution for a proof of correctness, but it's more than what the other people doing can do, because they don't have the ability just to run the big step and the small step semantics directly as generated. So to finish off with, we're doing more experiments on literature examples, but we want to move to bigger, more realistic languages. And the obvious one to look at, or let's say a very interesting one to look at, is Blasi and Leroy's C-light big steps semantics for a large, significant, interesting fragment of C. And this was the basis of the certified C compiler that Leroy's famous for. So what we would like to do is to translate this to small step semantics, because that will look a lot more like a machine. Small step semantics is much more related to a machine execution, going from state to state to state. So I think it will be an interesting experiment to do, first of all, to thoroughly test the transformation, the technique, and secondly, to then compare with this Blasi and Leroy's development and proof of the equivalence of the big step semantics to some execution level representation of the same program. We're doing the same thing. I don't expect there to be an initial exact correspondence, but I think it will enable us to gain some interesting insights into what's going on. So I've mentioned that we don't have a proof of correctness of the interpreter, and I could give you a hand-waving argument, but that's obviously a gap that has to be filled if we continue this work and write a full paper. And I think it will be more straightforward and transparent than proving the correctness of the transformations that other people have done. I think proving the correctness of the interpreter really just is much more directly related to the semantics rather than the mechanics of defunctionalization and continuations, parsing, and so on, which is the basis of the other work. We'd also like to look at variations of the interpreter for things like reduction semantics. When you talk to people about small step semantics, there's lots of different flavors of it, and sometimes you just get a value, and sometimes you have no environment, but just some sequence of expressions that's reduced, but they're all closely related, and I think we could do the same. It would be nice to show that the big step semantics was a basis for deriving various versions of small step semantics. And the other very interesting thing is, which I didn't even mention in the paper actually, although it was in the back of my mind, was the interpreter as written. You could criticize it as being somewhat artificial in the sense that we almost give a template of the small step rules, and then they're just instantiated by the rules. It would be more interesting to write a simpler interpreter that basically just linearly executed left to right the premises, moving on to the next one whenever you terminated. But then you need a more complex specializer to get the small step rules out of that. So there'd be a trade-off, an interpreter, a simpler interpreter that would be easier to prove correct, but then a more complex specializer that might be harder to prove correct, but the specializer is a much more generic tool based in the end on things like unfold fold transformations, which we know how to prove. We know how to use them to prove something like a partially evaluated correct. So I think this is where we would like to go. And that's it.
Thank you very much as well for the nice talk. To finish off Lobster, so questions. Where's a question?
Yeah, so the interpreters that you get, you mentioned that there's previous work that uses defunctionalization. Have you looked at how your interpreters, it looked like it introduced a bunch of these auxiliary syntactic forms. Is that the same case for these existing works?
Have I looked at what interpreters?
You mentioned the existing work that uses defunctionalization
Yes, yeah.
to do the same transformation. Does that introduce the same kind of syntactic forms as yours? I saw that there were a lot of different syntactic forms.
Well, yes. The two pieces of work that I've most closely compared with are Vesely and Fischer, who start with a definitional interpreter, a functional language incorporating the big step rules, and transform that via, I think, 10 stages, with starting off with the continuation, passing, transformation, and then defunctionalization. But in the end, a lot of those transformations are incorporated really in the specialization process. Also, the fact that we use a first-order language with a representation, a first-order representation of the big step rules in the interpreter. I didn't go into that, but I think then that the questions like defunctionalization disappear. Then it's just a question of an encoding of the rules, a suitable encoding. But the invention of the new constructors and so on, I think, is very similar in all the previous work. I mean, the other work is by Ambal, I think it is, in Aria, also starting from a definitional interpreter and transforming it. But at some point, they look at the continuation and say, in this case, we need to invent a new constructor to capture the continuation, and they define how a systematic way of doing that. So, not surprisingly, we're doing a lot of the same things, but I think as we say in the paper, we argue that this is an alternative way that is arguably more transparent than the transformation-based approach. But maybe it's a matter of taste also.
Oh, thank you.
So I guess we just thank the speaker and finish, and I guess I pass. Thank you very much.
Thank you very much. We have come to the end of this 33rd Lobster workshop here, and I'd like to take the opportunity to thank the authors of all submitted papers, the speakers, the invited speakers, the session chairs, and the participants in the room and also remotely, because without you and your active participation, this meeting would not work. And also it would not have worked for the last 33 conferences on this topic, so let's give everyone a hand. A meeting like this would also not work without the preparation of the meeting, and this includes all the PC members who have worked hard in reviewing all the submissions, engaging in the discussions. It would not work with our publicity chair, Daniel. Thank you very much for getting the call out. And also I would like to thank the local organizers, the video chairs, and all the volunteers, the student volunteers. Let's give them also a hand and thank them. You see, there are many people involved just to make this meeting work out. And I personally would like to thank also my PC co-chair who has been supporting Bishop Sankafle, who is supporting this meeting here right now from Australia in the background. And I think you all got his emails about the proceedings. There's a good chance also to remind you, if you're interested in getting printed material, printed proceedings from Springer, please send us your address and we'll manage to get Springer to send you the printed proceedings once they are done. Yeah, we have come to the end of this Lobster, but not to the end of the Lobster series of conferences, and our steering committee chairman will now present you more about what goes on.
Thank you, Robert. So actually, I'd like to add to the list of people to thank Robert Gluck, who ran everything in a very smooth way, and he did a lot of work together with, of course, Bisok-san, who couldn't be here. Okay, so Lobster 2023 is over, but life continues. So let's see if I can show you something or not. Let me see, presentation. Great. So next Lobster 2024 will be again co-located with PPDP, and together we will be in Milan, Italy, from 9 to 11 September 2024, hosted by the Formal Methods Conference of FME, which is the Formal Method Europe Association. Okay, so see you in Milan, and start thinking and writing papers to submit to Lobster 2024. Okay, thank you.